This is how the most popular spreads are created inside large-scale food factories. Peanuts are roasted and crushed into smooth spreads. Hazelnuts are blended with cocoa into rich paste, and strawberries are heated and set into glossy jam through tightly controlled processes. In this documentary, we follow the industrial systems and precision methods that convert ingredients into the best-tasting spreads on planet Earth. Peanut butter production begins with the bulk intake of raw, shelled peanuts delivered in containers or silos. Peanuts are gravity-fed into hopper systems equipped with vibratory feeders that control the rate of flow into the cleaning section. Cleaning involves sequential mechanical separation units, including air classifiers, rotary drum screens, and gravity tables. Air classifiers remove lightweight debris using high-velocity airstreams. Rotary screens separate based on particle size, discarding small fragments, sticks, and foreign seeds. Gravity tables use differential vibration and airflow to isolate denser whole peanuts from lighter defective material. Cleaned peanuts are transferred via bucket elevators into temporary storage bins prior to roasting. Roasting is carried out in continuous belt roasters or rotary drum roasters depending on line capacity. Peanuts are conveyed in a single layer through a thermal tunnel with forced hot air. Drum roasters use direct heat combined with rotating tumbling action. Roasting temperature ranges from 160 degrees Cs to 180 degrees Cs, with residence times of 25 and 40 minutes. Moisture sensors at the exit point ensure target moisture reduction to below 2%. Roasting also develops flavor and reduces microbial load. Cooled air is forced across the roasted peanuts immediately upon exit. Cooling conveyors equipped with perforated belts and axial fans reduce peanut temperature to below 35 degrees Celsius to prevent oil migration or condensation. Peanuts are held in cooled hoppers with agitation to prevent bridging before entering the blanching process. Blanching removes the outer skin and splits the peanuts. This is performed in two ways: dry blanching or water blanching. Dry blanching involves friction rollers that rub off the skins as peanuts pass through serrated cylinders. Water blanching involves immersion in hot water, followed by belt conveyors fitted with rubber rollers. In both methods, skin fragments are removed by aspiration or vacuum collection systems. Split peanuts pass through inspection belts or optical sorters to remove discolored, moldy, or damaged halves. High-speed cameras scan each peanut and trigger air jets to divert off-spec material. Sorted peanuts are collected in surge hoppers and metered into grinders. Peanut grinding is performed in two stages: primary size reduction and emulsification. The first stage uses a hammer mill or disc attrition mill. Peanuts are fed into a chamber with rotating blades or abrasive plates. The initial grind reduces particle size to around 300-500 microns. The paste is then pumped into a second stage colloid mill. The colloid mill performs high shear homogenization between a rotor and stator, reducing particle size to below 100 microns. Rotor speeds exceed 3000 RPM, and the grinding gap is adjustable for texture control. The grinding process also generates frictional heat, raising product temperature to 60-80 degrees Celsius, which reduces viscosity and facilitates emulsification. During the second stage grinding, or immediately afterward, stabilizing agents and additives are introduced. Common stabilizers include fully hydrogenated vegetable oils, such as rapeseed or cottonseed oil. These are pre-melted in jacketed tanks and dosed using heated transfer pumps. Stabilizer addition typically ranges from 1 to 2% by weight and is controlled with flow meters. For sweetened or flavored varieties, additional ingredients such as sugar, salt, molasses, or cocoa powder are added through powder feeders or liquid dosing pumps. These materials are pre-weighed and incorporated in line using dynamic mixers with static mixing elements or turbine blades to ensure rapid dispersion into the viscous peanut paste. After additive incorporation, the peanut butter undergoes a degassing phase. The hot paste is transferred to a vacuum chamber or degassing tank where air bubbles are removed. The system applies vacuum pressure between 0.7 and 0.9 bar while slowly agitating the product to avoid entrapping more air. This step improves texture and packaging stability. Degassed product flows into surge tanks equipped with slow-speed agitators and thermal jackets to maintain fluidity. Temperature is held between 55 to 65 degrees AS to facilitate downstream handling. Product is then directed toward the packaging line via sanitary lobe pumps, which provide high volume transfer without shear. Before filling, the peanut butter may be passed through a scraped surface heat exchanger to adjust temperature precisely. The system uses rotating scraper blades inside a jacketed tube to maintain heat transfer efficiency without fouling. Outlet temperature is held constant, typically 50-55 degrees Celsius, for optimal flow into containers. Packaging is performed on high-speed, servo-driven filling lines. Empty jars made of PAT or PP plastic are depalletized and placed onto the conveyor. Each jar passes through an ionized air rinser that removes particulate matter. Clean jars are indexed into a rotary filler with multi-nozzle heads. Volumetric piston fillers or mass flow filling systems dispense precise quantities of peanut butter into each jar. Fill levels are controlled within plus 0.5% tolerance. Nozzles are heated or jacketed to prevent clogging due to cooling product. Some systems use bottom-up filling to prevent air entrapment and surface voids. After filling, jars proceed to the capping station. Caps are sorted and aligned using centrifugal feeders or vibratory bowls, then applied and torqued by rotary chuck cappers. Torque sensors monitor seal integrity, and improperly sealed jars are rejected automatically. If induction sealing is required, a foil liner is placed inside the cap. After capping, jars pass under an induction sealer where a high-frequency electromagnetic field heats the foil, bonding it to the jar rim. The seal creates a hermetic barrier that prevents oxygen ingress and oil separation. Labeled jars move to a wraparound or pressure-sensitive labeling station. Labels are applied using servo-controlled applicators, and optical sensors verify alignment and barcode presence. Rejected units are diverted to inspection lanes. Coded printing systems, typically thermal inkjet or laser, apply batch numbers and date codes to the lid or shoulder of each jar. The print system is synchronized with the conveyor speed to ensure clear, consistent marking. Jars are grouped into sets using collation conveyors and loaded into corrugated cartons or shrink-wrap trays. Case packers use robotic arms or mechanical pushers. Sealed cases are labeled with logistic codes and moved to palletizers. Palletizing systems stack cases using programmed layer patterns. Slip sheets are added as needed, and completed pallets are stretch-wrapped with plastic film to stabilize the load for transport. Each pallet receives an RFID tag or barcode label for warehouse tracking. Throughout production, inline sensors monitor critical parameters. These include product temperature, flow rate, fill weight, torque, seal integrity, and label placement. Data is logged by the Central Manufacturing Execution System and linked to batch tracking systems for traceability. Process water used in cleaning and ingredient dissolution is stored separately and heated as needed. All process equipment is connected to CIP systems that circulate detergent and rinse solutions through pipes, tanks, pumps, and valves at scheduled intervals. Cleaning sequences are validated using conductivity, temperature, and flow sensors. Environmental conditions such as air, temperature, humidity, and particulate levels are regulated in processing areas using HVAC systems with HEPA filtration. Maintaining a controlled environment prevents moisture pickup by roasted peanuts and ensures consistent flow behavior of the peanut paste during grinding and filling. Roasting profiles are monitored using thermal sensors and data loggers. Temperature curves are logged and compared against reference curves to ensure even development across peanut batches. Real-time moisture analyzers positioned at the roaster exit verify dehydration targets. Particle size of the final peanut butter is measured using laser diffraction or sieving techniques. Target particle size is typically below 30 microns for smooth varieties and above 100 microns for crunchy variants. Crunchy peanut butter includes the addition of roasted peanut granules, which are prepared separately using coarse grinders, and added post-homogenization under low shear to maintain particle integrity. Oil. Separation resistance is measured during quality control using centrifuge testing or accelerated shelf life studies. Stabilizer effectiveness is confirmed through oil migration testing at elevated temperatures over time. Nutella production begins with the individual preparation of its components: hazelnuts, sugar, cocoa powder, vegetable oil, skimmed milk powder, lecithin, and vanillin. Each raw material is handled separately in dedicated systems to ensure proper particle size, mixing compatibility, and thermal behavior before integration. Hazelnuts are received shelled and pre-cleaned. They are conveyed through pneumatic lines into vibratory feeders that regulate flow into pre-roasting storage silos. From these silos, hazelnuts are metered into a continuous roasting system. Roasting occurs in horizontal convection tunnels or rotating cylindrical chambers, typically at 140 degrees 160 degrees C for 20-25 minutes, depending on kernel moisture. The goal is to reach a final moisture level below 2% and to initiate flavor development. Post-roasting, nuts are directed into cooling drums or belt coolers. Forced ambient air lowers kernel temperature to below 30 degrees Celsius before further handling. The next step is blanching, where the brown skin is removed. This is done using mechanical friction rollers or pressurized steam exposure, depending on the desired throughput. Skin is separated by aspiration. The blanched nuts are then split and sorted by size via oscillating sieves, and undersized fragments are diverted. Cleaned, roasted hazelnuts are passed through a primary grinding phase using disc mills or pin mills to produce a coarse meal. This intermediate product is directed into a secondary grinding stage, often a ball mill or high-speed impact mill, which reduces particle size to a fine paste. Typical particle sizes are reduced to under 30 microns at this stage, producing a flowable hazelnut slurry with partial oil release. In parallel, sugar is handled separately. Granulated sugar is milled using air-classifying impact mills to reduce particle size and ensure dissolution in the final product. The resulting fine sugar powder is transferred pneumatically to dosing silos. A similar dry handling system is used for skimmed milk powder, which is fed into mixers via enclosed screw conveyors. Cocoa powder is stored in low humidity silos and transferred through sealed auger systems to prevent moisture absorption. It is typically defatted and pre-sifted to avoid clumps or oversized particles. All powdered ingredients, sugar, milk, and cocoa, are dry blended using horizontal ribbon blenders. These blenders operate at low speed to achieve uniform mixing without generating excess dust. The vegetable oil, primarily refined palm oil, is kept in liquid state in temperature-controlled storage tanks maintained at 45 to 50 degrees C. Oil is pumped through inline filters and metered into mixing systems via flow control valves. The oil acts as the continuous phase for the final emulsion and must be dosed with high consistency. All components are transferred into a batch mixing system, a stainless steel planetary mixer, or a high viscosity processing vessel equipped with anchor agitators. The sequence starts with oil and hazelnut paste, followed by gradual incorporation of the powdered mix. Agitation is applied in stages, with high torque, low speed mixing used for initial wetting and medium speed agitation for full dispersion. Lecithin, added to control emulsion stability and flow, is stored in small heated tanks and introduced last. It is pre-mixed with a portion of the oil phase and dosed via peristaltic or gear pumps. Concentration is typically around 0.3% of the total mass. Vanillin, in synthetic form or as part of a flavoring premix, is injected at low concentrations and blended briefly under vacuum to prevent volatilization. The batch undergoes a refining stage using a 5-roll or 3-roll mill. The paste is pressed through steel rollers, reducing particle agglomerates and improving surface smoothness. The rollers operate at progressively higher speeds to create shear differentials, compressing solids and distributing fat evenly. Target final particle size is below 25 microns. After refining, the product is transferred to a conche, a jacketed horizontal mixer equipped with large mixing blades. The conching phase continues kneading at elevated temperatures of 50-60 degrees Celsius for 1 to 3 hours. This step enhances mouthfeel, disperses volatile compounds, and improves gloss by coating all particles with fat. Upon completion, the paste moves to a vacuum degassing tank where trapped air is removed. Vacuum is applied at 0.8 to 0.9 bar, while slow paddles maintain circulation. This step prevents air pockets in packaging and reduces oxidative degradation. The degassed product is homogenized through a low shear inline mixer to stabilize viscosity. The finished spread is transferred via jacketed pipelines to holding tanks prior to filling. These tanks are fitted with variable speed agitators and are temperature controlled at 40-45 degrees Celsius. A load cell system measures tank contents, coordinating flow to the packaging line. Transfer is performed with sanitary-grade rotary load pumps for accurate low shear movement of viscous material. In the filling area, jars are supplied via unscramblers and aligned onto conveyors. They pass under vision cameras to confirm shape and cleanliness. Filling is done using servo-controlled piston fillers or mass flow metering systems. Fill nozzles are jacketed and temperature controlled to maintain flow characteristics. Fill volumes are typically accurate to within plus 0.5%. After filling, jars are sealed with aluminum foil using induction sealing. A liner is embedded inside each cap. When the cap is torqued onto the jar and passed under the induction head, an electromagnetic field heats the foil, bonding it to the jar rim. This creates an oxygen barrier and prevents oil migration. Caps are applied using rotary or inline capping machines with torque monitoring. If torque deviates from preset values, jars are rejected. Sealed jars move to the labeling station, where pressure-sensitive or shrink-wrap labels are applied. Labeling heads are adjusted for jar geometry and verified by optical sensors. Next, jars are passed under thermal inkjet printers, which apply date codes and batch identifiers. Printers are aligned with conveyor timing to ensure sharp, legible printing. Codes are verified by barcode readers or OCR systems. Rejected jars are diverted using pneumatic pushers. Labeled jars are grouped into sets using automated collation conveyors. Depending on destination, they may be packed into cardboard cartons or shrink-wrapped into trays. Cartoning machines erect boxes, load jars, and apply closure glue automatically. Case packers then arrange cartons into shipping cases with robotic arms. Shipping cases are sealed using hot melt glue applicators or tape dispensers and labeled with printed logistics data. The labeled cases are scanned, weighed, and conveyed to a palletizing station. Robotic palletizers stack cases according to optimized patterns, using vacuum or mechanical end effectors. Pallets are wrapped using rotary arm stretch wrappers. Film is tensioned to maintain structural integrity without distorting the cartons. Pallets are tagged with scannable barcodes or RFID labels for traceability. Throughout the entire production process, all operations are controlled and logged by a PLC-driven SCADA system. This includes ingredient dosing, thermal profiles, particle size measurements, fill volumes, torque levels, and packaging throughput. Parameters are displayed on HMI terminals and stored in batch records for traceability. Strawberry jam manufacturing begins with bulk delivery of strawberries in refrigerated containers. The fruit arrives pre-sorted or in raw form depending on source. Upon unloading, strawberries are tipped into stainless steel flume tanks where they are submerged in chilled water to reduce field heat and initiate washing. The strawberries are conveyed out of the wash tank using cleated food-grade belt elevators. A high-pressure spray bar located at the discharge point removes surface contaminants. Excess water is removed by air knives or centrifugal dewatering systems. Cleaned fruit is conveyed to the inspection station. At the inspection stage, strawberries pass over a slow-moving belt or roller table equipped with manual or optical sorters. Defective, underripe, or foreign objects are removed. High-resolution cameras with multispectral imaging may be used for automatic defect detection. Rejected items are separated using pneumatic actuators or diverters. Clean, sorted strawberries are directed to the hulling station. Hulling machines use rotating rubber fingers or mechanical plungers to remove the calyx and stem. The removed portions are separated by air aspiration. Hulled fruit is transferred to a temporary buffer hopper before size reduction. The hulling hopper meters strawberries into a dicing or pulping system. Dicing machines use oscillating blades to produce uniform fruit pieces. For homogeneous jam, fruit is passed through a finisher or pulper equipped with perforated screens and rotating paddles to produce a consistent puree. Screen aperture determines the level of texture in the final product. Pulpy fruit mass is weighed using inline load cells or flow meters and directed to a batching tank. In parallel, sugar is conveyed from silos or bulk bags into a dry blending unit. Sugar is sometimes preheated or dissolved in deionized water to create a syrup. This is controlled by mass flow regulation and prepared in jacketed mixing tanks equipped with agitators. Pectin is added either as a powder or as a pre-dispersed liquid. Powdered pectin is mixed with a portion of sugar to prevent clumping during hydration. The blend is fed into the batching tank via screw feeders or high shear dispersers. The type and concentration of pectin depend on the desired gel strength and fruit acidity. Citric acid is introduced to adjust pH, typically to the range of 3.1-3.4, which optimizes pectin gelation. Acid is dosed from a separate tank using peristaltic pumps monitored by inline pH probes. The exact amount is calculated based on the natural acidity of the strawberry pulp, which is measured per batch. In certain formulations, calcium salts may be added to activate low methoxyl pectins. These are metered in precise amounts using microdosing pumps. Water content is balanced by calculating the moisture level of incoming fruit and adjusting with deionized water or fruit juice concentrates. The full formulation, strawberry mass, sugar, pectin, acid, and optional additives, is transferred to a batch vacuum cooker. The cooking vessel is a steam-jacketed stainless steel kettle, often equipped with an anchor agitator and a central high-shear rotor for uniform heat transfer and reduced localized scorching. Cooking parameters are set to evaporate excess moisture, invert part of the sucrose, and activate pectin. The process is performed under partial vacuum to allow boiling at lower temperatures, preserving color and flavor while reducing thermal degradation. Typical target solids content for jam is 65-68 degree brix, measured with inline refractometers. During cooking, water vapor is extracted through a condenser system connected to the vacuum circuit. Condensate is collected and removed via gravity drains or vacuum traps. The jam mass is circulated continuously through the cooker using sanitary centrifugal pumps. This ensures uniform heating and prevents sedimentation of fruit particles. Once the desired brix and viscosity are achieved, the batch is cooled through a scraped surface heat exchanger. This unit has a rotor with fixed blades that continuously remove product from the heat transfer surface, enabling rapid cooling while preventing fouling. Product temperature is reduced to below 85 degrees Celsius to prepare for filling. Deaeration is performed inline or in a separate vacuum tank. This step removes entrained air bubbles introduced during cooking and agitation. Vacuum is maintained at approximately 0.8 bar, while slow agitation is applied to stabilize the product's density and texture. Optional flavoring agents or color corrections are added at this stage. Natural strawberry flavors or concentrated fruit essences are introduced through metering systems. Any added color is dispersed into a small portion of jam and blended thoroughly to prevent streaking. The final mixture is homogenized using low shear mixers to avoid foam generation. Finished jam is held in surge tanks equipped with level sensors, slow-speed agitators, and thermal jackets to maintain flowability. Surge tanks are connected to the filling system via positive displacement pumps or rotary lobe pumps that handle viscous products with suspended solids. Glass jars or plastic containers are depalletized and transferred to the filling line using timing screws and indexing star wheels. Containers are first rinsed with filtered air or ionized air jets. Jars are checked by vision systems for cleanliness and structural integrity. Jam is filled hot, usually between 80-85 degrees Celsius, to enable vacuum sealing after capping. Filling is performed using piston fillers or mass flow-based servo systems. Fill volume is precisely controlled to match container dimensions and headspace requirements. Foaming is minimized by diving nozzles that dispense product near the base of the container. Immediately after filling, containers pass through a capping station. Metal twist-off caps with vacuum buttons or plastic snap-on lids are applied by mechanical torque heads. For metal closures, steam injection may be used just before capping to displace air and create a vacuum as the container cools. Capped jars move through an inverted holding tunnel or a rotary cooling system. Cooling is carried out using ambient air or chilled water sprays to bring the product below 40 degrees Celsius. Gradual cooling prevents thermal shock to containers and promotes vacuum formation in sealed jars. Vacuum level is verified through cap button testing. Non-vacuum jars are automatically rejected. Labeling follows cooling. Jars are dried using air knives or infrared heaters before entering the labeler. Labels are applied using pressure-sensitive or hot melt glue systems, depending on the label substrate and application speed. Coded information such as production date, expiration, and batch number is printed using thermal inkjet or laser coders. Print location and clarity are verified by high-speed vision systems. Jars failing print quality checks are removed from the line. Labeled jars are grouped into cartons using robotic pick-and-place arms or mechanical collators. Cartons are formed from flat blanks, glued, and sealed using flap folders and glue guns. Carton integrity is checked by sensors measuring weight and dimensions. Cases are packed into shipping boxes or trays. Box formers erect corrugated cases, which are filled and sealed on a continuous motion line. Finished cases are conveyed to an automated palletizer, which stacks them in configured patterns for optimal stability. Pallets are conveyed to a stretch wrapping system where film is applied under tension. Each pallet is labeled with a scannable ID, linked to batch and traceability data. Wrapped pallets are moved to staging zones for distribution or temperature-controlled storage. Throughout the process, control systems monitor and log all variables. Programmable logic controllers manage dosing, cooking, filling, and packaging operations. Sensors measure temperature, flow, pressure, and viscosity. Human-machine interfaces provide operators with real-time control and alarms. Brix levels are verified at multiple points using digital inline refractometers. pH is measured with inline glass electrode probes. Final jam consistency is evaluated using rotational viscometers or Bostwick consistometers. Water activity meters confirm product stability. Toothpaste production begins with the batching of raw materials into three primary categories: abrasives, humectants, and active ingredients. These components are stored in bulk silos, intermediate bulk containers, and stainless steel drums positioned adjacent to the central mixing facility. Ingredient delivery is managed through automated vacuum conveyors, liquid transfer pumps, and weigh-scale monitored feeders. Abrasives are typically calcium carbonate, hydrated silica, or dicalcium phosphate dihydrate. These powders are conveyed through enclosed pipelines and loaded into high-shear mixing vessels fitted with load cells. Particle size of abrasives is controlled within 5 to 15 microns for optimal cleaning performance without excessive enamel wear. The feed rate is calibrated by rotary valve controllers. Humectants, primarily sorbitol solution, glycerin, and propylene glycol, are stored in temperature-controlled, jacketed tanks. These are pumped into the mixer through flow meter regulated dosing lines. The purpose of humectants is to retain moisture, maintain paste consistency, and prevent drying inside the tube. Viscosity and density of each liquid are tracked by inline sensors during transfer. Deionized water is introduced in precise volume based on formulation requirements. The water is pre-treated via reverse osmosis filtration and UV sterilization, then dosed into the batch using mass flow controllers to ensure accurate hydration of solids. Active ingredients such as sodium fluoride or stannous fluoride are pre-blended in secondary mixing tanks before being introduced to the main mixer. These compounds are sensitive to pH and temperature, requiring separate handling. Dosing is performed using positive displacement pumps to achieve concentrations typically around 0.24% for fluoride ion. A surfactant, usually sodium lauryl sulfate, is added last due to its foaming and emulsifying properties. It is introduced in liquid or paste form through heated lines maintained at 30-35 degrees Celsius to reduce viscosity. SLS is blended gently to avoid excessive aeration. The target inclusion level ranges between 1.0–2.0% depending on the formulation. Hydrocolloid binders such as carboxymethyl cellulose, xanthan gum, or carrageenan are pre-dispersed in warm water before being added to the mixture. These agents control rheology and prevent phase separation. Dispersion tanks use overhead agitators operating at low RPM to avoid clumping. Hydration time is monitored to ensure full polymer expansion before integration. Flavoring oils like spearmint or peppermint are stored in sealed drums and introduced through small volume dosing systems equipped with peristaltic pumps. Flavors are highly concentrated and dosed between 0.3–0.7% by weight. The addition is carried out under vacuum to prevent volatilization. Colorants such as titanium dioxide or FD&C dyes are added as aqueous slurries or predispersed concentrates. These are introduced late in the mix cycle for visual uniformity. Color matching is performed using spectrophotometric sensors positioned above the mixing vessel. Once all materials are loaded, the main batch undergoes high shear mixing. The vessel uses multi-stage impellers, typically a bottom-mounted anchor blade for macro movement and a rotor-stator head for localized dispersion. Mix time ranges from 30 to 45 minutes. Viscosity is continuously measured via in-tank torque sensors and correlated to predefined set points. The entire vessel is held under partial vacuum to remove entrained air. A vacuum pump system pulls air through condensers and liquid traps. Vacuum mixing prevents bubble formation, ensures uniform density, and improves the shelf stability of the final product. Once the batch reaches target viscosity and homogeneity, a recirculation loop begins. The mixture is pumped through inline homogenizers or colloid mills to further reduce particle size and eliminate agglomerates. Homogenization shear rates exceed 10,000 S1, providing a consistent microstructure. The homogenized toothpaste is filtered through stainless steel mesh screens, typically 80 to 120 mesh size, to remove any foreign particles or unblended residue. The product is discharged into vacuum-holding tanks equipped with slow-speed agitators to maintain consistency while awaiting packaging. The filling process begins with the transport of toothpaste from holding tanks to the filling line through sanitary diaphragm pumps and flexible hoses. The product is kept under continuous agitation to prevent settling of heavier components. Tubes, either laminate, aluminum, or co-extruded plastic, are loaded into an orienting magazine. Tubes are fed one by one into indexing star wheels that position each unit beneath the filling nozzle. Optical sensors ensure correct alignment based on pre-printed registration marks. Filling nozzles are submerged slightly into each tube and retract upward during discharge to prevent air pockets. Volumetric filling pumps dispense the product in quantities typically ranging from 75 ml to 150 ml. Fill weight is controlled to plus 1% using servo-driven piston pumps or mass flow metering systems. Immediately after filling, the tube passes to the sealing station. For laminate or plastic tubes, the tail is heat sealed using conduction or impulse sealers. The sealing bars clamp the tube end, applying pressure and heat to fuse the inner layers. For aluminum tubes, the tail is folded and crimped mechanically by a multi-head crimping tool. A batch code and timestamp are embossed or inkjet printed onto the sealed end. This information includes production line, time, and lot number for traceability. The print heads are aligned with the tube transport belt and are capable of printing at over 300 units per minute. Filled tubes are ejected onto a conveyor and enter a carton loading station. Flat-folded cartons are erected using vacuum grippers and mechanical pushers, then held open under guide rails. Each tube is inserted automatically, and informational leaflets are added if required by formulation. Cartons are closed using hot melt glue applicators or tuck-in flaps depending on design. Sensors verify the presence of a tube inside each carton. Incomplete units are automatically rejected through diverter arms. Cartons are grouped into shipping cases via a robotic case packer. Cases are assembled from flat blanks, filled, and sealed using hot glue or tape. Case labels are printed and applied using print and apply applicators with real-time data from the production control system. Completed cases are moved onto a palletizer conveyor. An articulated arm robot stacks cases onto pallets in a predefined pattern. Slip sheets are inserted automatically between layers to maintain stability. Full pallets are stretch wrapped using rotating ring or arm wrappers. The film tension and overlap are adjustable to prevent compression of cartons while ensuring unit load integrity. Pallets are labeled on two sides with shipping and tracking information. Barcode scanners verify label accuracy and update inventory systems. Pallets are then transferred to staging zones for warehousing or direct shipment. During production, the entire process is governed by a centralized control system. Each piece of equipment is connected through a SCADA network, allowing operators to monitor tank levels, batch status, mix parameters, and fill rates from an HMI panel. Ingredient weighing stations utilize barcode scanners and recipe control software to prevent cross-contamination and ensure formula compliance. Any deviation from programmed weight tolerances triggers an alarm and locks further processing. Rheological properties are tested in real time using rotational viscometers. Samples from each batch are drawn via sampling ports and analyzed for yield stress, viscosity at shear, and thixotropy to confirm product performance. pH levels are measured with inline electrodes during mixing, typically targeting a range of 6.5 to 7.5, depending on the actives used. Fluoride ion concentration is verified using ion-selective electrodes to confirm dosing accuracy. Toothpaste density is measured using vibrating tube densitometers, and compared against target values to ensure proper tube filling weight. Deviations are corrected by adjusting water content or mixing parameters. Color uniformity is monitored using inline spectrophotometers calibrated to CIE lab. Color space standards. Any deviation beyond preset delta E values prompts batch correction or rejection. Each major tank and mixer is equipped with CIP systems consisting of rotating spray balls, detergent feed lines, and automated rinse cycles. CIP cycles are logged in the MES to maintain batch integrity. Final packaging lines are equipped with vision systems to detect carton defects, misalignment, or barcode errors. These systems use high-resolution cameras and rejection logic to divert non-conforming packages. High-speed toothpaste production lines are capable of producing over 300 tubes per minute, with batch sizes ranging from 1,000 to 6,000 liters depending on demand. Formulation changes are executed by software-driven recipe management with automated valve sequencing and ingredient routing. Mouthwash production begins with the preparation of purified water, which serves as the base solvent for all ingredients. The water undergoes reverse osmosis, filtration, followed by ultraviolet sterilization. Conductivity meters and microbial sensors ensure that the water meets pharmaceutical grade specifications before being stored in stainless steel holding tanks equipped with continuous recirculation systems to prevent stagnation. Batch production starts with loading water into a stainless steel jacketed mixing vessel fitted with high shear agitators. The vessel is mounted on load cells to allow for precise weight-based dosing of each component. All ingredients are added in a controlled sequence based on formulation parameters pre-programmed into the batch control system. Humectants are added first. Glycerin, sorbitol solution, or propylene glycol is pumped from storage tanks using metered diaphragm pumps. Flow meters and temperature sensors track each transfer. These compounds help retain moisture and provide viscosity and sweetness. Typical inclusion ranges from 5 to 25% by weight. Alcohol, when used as a solvent and preservative, is added next. Ethanol is transferred from explosion-proof storage tanks through stainless steel piping. The addition is performed under closed-loop nitrogen-blanketed conditions to minimize evaporation. Flow rate is monitored by mass flow meters, and volume is logged digitally for each batch. Final ethanol concentration typically ranges from 15 to 27% in alcohol-based formulations. Active ingredients are added once the base solution stabilizes. These include antimicrobial agents such as cetylpyridinium chloride, chlorhexidine gluconate, or essential oil blends. Active ingredient dosing is highly precise and performed using peristaltic pumps from sealed ingredient totes. Target concentration is verified using inline UV absorbance detectors or conductivity probes depending on the compound. Fluoride compounds, such as sodium fluoride or stannous fluoride, are prepared as pre-dissolved concentrates in separate mixing tanks using deionized water. These are dosed into the main batch at levels typically ranging from 225 to 1000 ppm fluoride ion. Addition is done slowly to avoid precipitation, and pH is adjusted immediately. Afterward, to maintain stability. Flavoring agents are next. These include mint oils, cinnamon, or eucalyptus derivatives. Essential oils are highly volatile and introduced using closed-loop pumps with nitrogen pressurization. Solubility is aided by pre-mixing oils with non-ionic surfactants or alcohol carriers before addition. Colorants are added in the form of water-soluble dye solutions or color dispersions. Each colorant is pre-weighed and diluted before dosing. Magnetic stirrers or inline static mixers ensure uniform dispersion. Optical sensors may be mounted over the mixing tank to confirm target lab or chess color values in real time. Preservatives such as methylparaben, propylparaben or sodium benzoate are added next. These are introduced as aqueous solutions prepared in separate blend tanks. Preservative concentration ranges from 0.05–0.2% depending on product shelf life requirements and microbial load assessments. Addition is carried out under agitation to ensure full dissolution. Sweeteners such as sodium saccharin, xylitol, or sucralose are added to enhance palatability. These are dosed in small concentrations, typically below 0.5%, using high-precision auger feeders or micro-piston pumps depending on the form. Mixing continues at low speed to prevent foaming. The final mouthwash formulation is adjusted for pH. Aqueous solutions of sodium hydroxide or citric acid are prepared in auxiliary tanks and dosed using digital peristaltic pumps. pH is continuously monitored by inline probes to maintain a range typically between 4.5 and 7.0, depending on the active ingredients and flavor profile. Anti-foaming agents are optionally added during the final mixing phase. These include dimethicone emulsions or food-grade silicone oils. Addition is controlled via gear pumps and only applied when foaming exceeds threshold levels, as detected by capacitive foam sensors inside the vessel. After full ingredient incorporation, the batch is subjected to a recirculation loop using a centrifugal pump system. The liquid is passed through an inline homogenizer or static mixer to eliminate stratification and achieve consistent texture and solute distribution. The blended product is filtered through sanitary-grade filtration systems, typically consisting of 5 to 10 micron nominal filters, followed by 0.45 micron absolute membrane filters. Filters are housed in stainless steel vessels with differential pressure gauges to monitor clogging. Filtration removes undissolved solids and potential contaminants prior to packaging. Filtered mouthwash is then transferred via sanitary pipelines to intermediate storage tanks or directly to the filling line. Holding tanks are jacketed and equipped with low shear agitators to maintain homogeneity. Each tank includes a vented filter to preserve sterility and pressure balance. Bottling begins with automatic bottle unscramblers that orient and feed empty bottles onto the production conveyor. Bottles are conveyed under a rinsing station where filtered air or ozonated water is sprayed into each bottle via nozzle inserts. Rinse nozzles retract after each cycle, and residual rinse is removed using vacuum-assisted drainage. Clean bottles move to the filling carousel. Volumetric or flow meter-based filling systems dispense liquid into each bottle. Nozzles are equipped with anti-drip valves and may dive into the bottleneck to minimize turbulence. Fill volumes are controlled to within +1 ml using servo-controlled pistons or mass flow controllers. Line speeds may exceed 200 bottles per minute depending on bottle size and product viscosity. Filled bottles proceed to the capping station. Caps are sorted via a centrifugal feeder or vibratory bowl and oriented into a chute. A pick-and-place system applies each cap to a bottle, and servo torque heads tighten the cap to precise specifications. Torque monitoring systems verify seal integrity for each unit. Induction foil sealing may be used, especially for alcohol-based or high-value formulas. Bottles pass under an induction coil, which heats the foil liner inside the cap. The foil bonds to the bottle, rim through localized heat and pressure, creating a tamper-evident, leak-proof seal. Labeled bottles proceed through a pressure-sensitive labeling station. Label spools feed through optical sensors and tensioning arms. Each label is applied to the bottle using rubber rollers or air jets and wrapped around the circumference. Vision systems verify label placement, orientation, and print quality. Optional shrink bands are applied for tamper evidence. Bands are dropped onto the bottlenecks and conveyed through a shrink tunnel heated by steam or infrared elements. Temperature control ensures uniform band shrinkage without damaging the label. Coated printing is applied next. Thermal inkjet or laser printers mark each bottle with batch number, timestamp, and expiration date. Printers are mounted on adjustable arms and synchronized with the conveyor motion to maintain legibility at high speeds. Bottles are collected into groups using pack-off tables or automated grouping conveyors. Depending on the packaging format, grouped bottles are transferred to a cartoner or case packer. Cartons are erected automatically, and bottles are inserted using push arms or robotic arms. Cases are formed using automatic case erectors. Cartons are loaded into corrugated shipping cases in a pre-programmed layout. Flaps are closed using hot melt glue or tape, and cases are labeled with shipping information using print and apply labelers. Completed cases are transported to palletizing systems. Robotic palletizers stack cases layer by layer using vacuum grippers or mechanical forks. Slip sheets are inserted as needed. Stack configurations follow warehouse layout and transport requirements. Each pallet is stretch wrapped using rotary arm or turntable systems. Stretch film is applied with controlled tension and overlap to stabilize the load. Barcode labels are applied to two adjacent sides for warehouse scanning. Throughout the entire production process, data is logged by a centralized manufacturing execution system. Ingredient usage, batch ID, tank temperatures, pH levels, fill weights, and cap torques are recorded in real time. Deviations outside of tolerance trigger automatic alarms and halt affected processes. Inline process analytical technologies are used for real-time monitoring of active concentration, color consistency, and microbial integrity. Ultraviolet spectrophotometers, or Raman probes, measure concentrations of key actives like fluoride or chlorhexidine without requiring sample removal. Inventory management systems track lot numbers of all raw materials and link them to finished product batches for traceability. Each component is barcoded and scanned before addition to a batch, ensuring compliance with formulation requirements. Shampoo production begins with the preparation of process, water, which functions as the primary carrier for all ingredients. Incoming water is treated through multi-stage filtration systems that include sand filtration, activated carbon beds, reverse osmosis membranes, and ultraviolet sterilization. Treated water is stored in stainless steel buffer tanks equipped with recirculation pumps to maintain uniform temperature and prevent stratification. The manufacturing process is typically batch-based, although some high-volume lines use semi-continuous systems. Each batch starts with charging a jacketed stainless steel mixing vessel with a calculated volume of purified water. The vessel is mounted on load cells that provide real-time mass data to the batch control system. Agitation begins immediately using a slow-speed anchor impeller to establish bulk circulation. Primary surfactants are added first. These are the main cleansing agents and usually include sodium laureth sulfate, sodium lauryl sulfate, ammonium laureth sulfate, or sodium cocoyl isethionate, depending on formulation. Liquid surfactants are pumped from storage tanks using variable speed, centrifugal, or positive displacement pumps. Flow is regulated by mass flow meters, and addition rates are synchronized with agitator speed to avoid excessive foaming. For formulations using solid or paste surfactants, the materials are pre-dissolved in auxiliary tanks. These tanks are heated via steam or hot water jackets to reduce viscosity and accelerate dissolution. High shear mixers are used to break down surfactant agglomerates before the solution is transferred into the main batch vessel. Once the primary surfactants are fully dispersed, secondary surfactants are introduced. These include cocamidopropyl betaine, sodium cocoamphoacetate, or other amphoteric surfactants that improve mildness and foam stability. These materials are dosed through metered pumps and blended under moderate agitation to ensure compatibility with the primary surfactant system. Thickeners, are added next to control viscosity. Depending on the formulation, these may include sodium chloride, ammonium chloride, hydroxyethyl cellulose, xanthan gum, or acrylate-based polymers. Salt-based thickeners are dissolved directly into the batch using controlled dosing, while polymeric thickeners are prehydrated in separate dispersion tanks to prevent lump formation. Polymer dispersions are slowly added under high shear conditions to ensure uniform distribution. Conditioning agents are incorporated after viscosity begins to develop. These include cationic polymers, such as polyquaternium compounds, guar hydroxypropyl trimonium chloride, or silicone emulsions. Silicone conditioning agents, such as dimethicone or amidimethicone, are supplied as stable emulsions and added under low shear agitation to prevent emulsion breakage. The batch temperature is carefully controlled, typically between 30–45 degrees C, to maintain emulsion stability. Pearlizing agents are added when a pearlescent appearance is required. These materials often consist of ethylene glycol, distearate, or glycol monostearate dispersions. Pearlizing agents are melted in heated side vessels and added to the batch at elevated temperature. Controlled cooling is then used to crystallize the pearlescent particles, producing uniform light-reflecting platelets throughout the shampoo. Chelating agents such as disodium EDTA are introduced to bind metal ions present in water or raw materials. These are added early in the process, usually dissolved in water, to improve product stability and preservative effectiveness. Dosing is managed using precision pumps due to the low concentration required. Preservatives are added once the surfactant system is fully established. These may include phenoxyethanol, sodium benzoate, potassium sorbate, or blended preservative systems. Preservatives are typically added as liquid concentrates and dispersed thoroughly under continuous agitation. The concentration is controlled to achieve microbial stability without affecting product performance. pH adjustment follows. Shampoo formulations generally target a pH range between 4.5 and 6.5 to align with hair and scalp compatibility. pH adjusters, such as citric acid or sodium hydroxide, are prepared as dilute solutions in auxiliary tanks. These solutions are dosed gradually, while pH is monitored using inline probes connected to the batch control system. Adjustments are made incrementally to avoid overshooting target values. Fragrance is added near the end of the mixing process. Fragrance oils are complex blends of aromatic compounds and are typically pre-dissolved in a solubilizer or surfactant base before addition. This prevents separation or clouding. Fragrance addition is carried out under low agitation to minimize volatilization and foaming. Dosing is controlled with high accuracy peristaltic pumps due to the low inclusion rate. Colorants are added as diluted solutions or dispersions. Liquid dyes are metered into the batch, while powdered pigments are pre-dispersed in water or surfactant solution to ensure uniform color distribution. Optical sensors or laboratory sampling is used to confirm color consistency against formulation standards. Once all ingredients are added, the batch undergoes a final homogenization phase. The shampoo is circulated through an inline rotastator mixer or colloid mill to eliminate microlumps, improve clarity, and ensure uniform viscosity. Shear rates are carefully controlled to avoid degrading polymer thickeners or breaking silicone emulsions. During homogenization, air entrainment is minimized. Some systems apply vacuum to the mixing vessel to remove entrapped air bubbles. Vacuum levels are controlled to prevent excessive evaporation of volatile components such as fragrance. After homogenization, the shampoo is transferred to a finishing tank. This tank is equipped with gentle agitation to maintain homogeneity while allowing the product to cool to filling temperature. Cooling is achieved via the vessel jacket using chilled water or ambient cooling loops. Final viscosity develops during this cooling phase, particularly for salt or polymer-thickened systems. Quality parameters are verified at this stage. Viscosity is measured using rotational viscometers, density is checked using digital densitometers, and pH is reconfirmed. Adjustments can still be made by adding small amounts of water, thickener, or pH modifier if required. The finished shampoo is then pumped through sanitary pipelines to the filling area. Transfer pumps are selected based on product viscosity and shear sensitivity, commonly using lobe pumps or progressive cavity pumps. Flow rates are synchronized with filling line demand to maintain steady supply. Packaging begins with bottle preparation. Empty bottles made from PET, HDPE, or PP are delivered to the line in bulk and fed into an unscrambler. The unscrambler orients bottles upright and transfers them onto a conveyor system. Bottles pass through an air rinsing station where filtered air removes dust or debris from the interior. Bottles are conveyed to the filling machine. Filling systems may be volumetric piston fillers, mass flow fillers, or time pressure fillers, depending on product viscosity and accuracy requirements. Filling nozzles descend into the bottleneck to reduce splashing and foaming. Fill volumes are controlled to tight tolerances, typically within plus 0.5%. Filled bottles move to the capping station. Caps are sorted and oriented using vibratory bowl feeders. Each cap is placed onto a bottle and tightened using torque-controlled capping heads. Torque values are monitored continuously to ensure consistent closure without deforming the bottle or cap threads. If induction sealing is used, bottles pass under an induction coil that heats a foil liner inside the cap. The liner bonds to the bottle rim, creating a hermetic seal. Coil power and conveyor speed are calibrated to ensure uniform sealing without overheating the product. Labeled bottles proceed to the labeling station. Labels may be pressure sensitive, shrink sleeve, or wraparound types. Pressure sensitive labels are applied using rollers and air jets, with registration controlled by optical sensors. Shrink sleeves are applied loosely and then passed through a heat tunnel where they conform tightly to the bottle shape. Batch codes and expiration dates are printed on the bottle or label using inkjet or laser coding systems. Print quality is verified by vision systems that detect missing or illegible codes and trigger rejection mechanisms. Bottles are then grouped for secondary packaging. Automatic packers collate bottles into predefined counts and load them into cartons or trays. Cartons are erected from flat blanks and sealed using hot melt adhesive. Case packers arrange cartons into shipping cases according to palletization requirements. Shipping cases are conveyed to palletizing systems. Robotic palletizers stack cases onto pallets in programmed patterns to maximize stability and space utilization. Slip sheets may be inserted between layers. Completed pallets are wrapped with stretch film to secure the load. Throughout the entire process, production is controlled by a centralized automation system. Programmable logic controllers manage ingredient dosing, mixing speeds, temperatures, and transfer operations. A supervisory control and data acquisition system provides real-time monitoring, data logging, and batch traceability. Recipe management software stores detailed formulation parameters, allowing rapid changeover between different shampoo variants such as moisturizing, clarifying, volumizing, or color protecting types. Automated valve manifolds route ingredients to the correct vessels based on the selected recipe. Raw material inventory is tracked digitally. Each ingredient lot is scanned and logged before use, and consumption data is automatically reconciled with production output. This ensures accurate material planning and batch traceability. Cleaning cycles between batches are executed using automated clean-in-place systems. These systems circulate cleaning solutions and rinse water through vessels, pipes, pumps, and fillers without disassembly. Cleaning parameters such as time, temperature, and flow rate are recorded for each cycle. Tim Hortons donut production begins with a dry mix formulation containing enriched wheat flour, sugar, dextrose, non-fat dry milk, salt, leavening agents like sodium acid pyrophosphate and baking soda, and dough conditioners. These dry ingredients are stored in silos or large bagged quantities and conveyed into industrial mixers via auger-fed hoppers. Water, maintained at a controlled temperature between 26-30 degrees C, is added automatically by volume through solenoid-controlled valves. The mixture undergoes a high-capacity mixing process using horizontal paddle mixers that operate for approximately 10 to 12 minutes until a smooth, elastic dough forms. Dough temperature is precisely maintained to ensure consistent gluten development. The mixed dough is transferred to a resting conveyor where it undergoes a short fermentation stage, typically lasting 10 to 15 minutes. During this period, gluten strands relax, allowing easier downstream sheeting and cutting. The dough enters a sheeting system composed of heavy-duty rollers that gradually flatten the dough to a uniform thickness, often between 8 to 12 millimeters depending on the donut type. A dusting system coats the sheet with a thin layer of flour or starch to prevent sticking. Next, rotary cutters mounted on a continuous belt use oscillating blades and die shapes to stamp out ring donuts, filled donut bases, and specialty shapes. Hole cutouts are collected via vacuum suction and reintroduced into the dough stream to reduce waste. The shaped pieces drop onto a mesh conveyor belt, which transfers them into a proofing chamber. The proofer is a humidity and temperature-controlled enclosure typically maintained at 38-42 degrees and 75-85% relative humidity. Here, yeast-leavened donuts undergo final fermentation for 35 to 50 minutes, doubling in size. Upon exiting the proofer, donuts enter a continuous fryer via an infeed belt that gently lowers each piece into the oil. The fryer is filled with high-stability vegetable shortening, held at a consistent temperature of 185-190 degrees C. Conveyor arms with paddles submerge the donuts briefly before flipping mechanisms rotate them halfway through the cycle to ensure even cooking on both sides. Each donut spends 120 seconds in the fryer. Oil filtration systems continuously circulate and clean the oil through mechanical filters and carbon filtration media to maintain clarity and extend oil life. Excess oil is removed from the surface by air knives as donuts exit the fryer. Fried donuts transfer to a cooling conveyor, where forced ambient air reduces product temperature before glazing or filling. For ring donuts, a waterfall-style glazing system coats the tops with sugar glaze. The glazing machine contains a recirculating pump that delivers a steady curtain of glaze to ensure uniform coverage. Filled varieties proceed to an injection station. A synchronized multi-nozzle injector aligns with each donut and dispenses a precise volume of filling, such as fruit jam, Bavarian cream, or chocolate, into the center of the pastry using piston-driven pumps. Fill volumes are regulated down to the gram for product consistency. Specialty donuts requiring additional coatings, such as powdered sugar or cinnamon sugar, enter a rotating tumbler. The tumbler's perforated drum allows excess sugar to fall through while evenly applying the coating as the donuts rotate inside. Sensors monitor rotation speed and coating application rate. For chocolate or icing-top varieties, donuts pass through a curtain enrobing system or a top-down depositor. The enrobing system consists of a tempering kettle and a heated pump that maintains the chocolate or icing at its working viscosity, typically around 40-45 degrees Celsius. Topping depth is controlled by belt speed and curtain thickness. Donuts requiring sprinkles or toppings are conveyed beneath a waterfall depositor or rotary sprinkler. The toppings are dispensed from a vibrating hopper that ensures even spread. Static charge may be applied in some systems to increase topping adhesion to the wet icing. Once decorated or filled, donuts proceed through a spiral cooling tower. The spiral conveyor allows a compact vertical footprint while offering extended cooling time, typically 15 to 20 minutes. Forced air circulation removes residual heat, allowing products to stabilize before packaging. Each donut then moves through a vision-based quality control system. High-speed cameras scan for defects in size, color, fill placement, or topping consistency. Items outside. Tolerants are rejected automatically using pneumatic pushers. Qualified donuts are then grouped by variety and type using a servo-controlled collation system. Products are aligned into lanes and counted by photoelectric sensors, preparing them for packaging. Packaging is handled by an automated tray loading system. Flat-folded paperboard trays are erected using mechanical arms, and donuts are placed inside via pick-and-place robots with suction grippers. For assorted packs, robotic arms select donuts by type from buffer conveyors. Trays proceed to a lid applicator station, where pre-folded lids are pressed and sealed using glue jets or heat-sensitive adhesives. For retail cases, sealed trays are grouped and shrink-wrapped using polyolefin film, which is cut, wrapped, and heat-shrunk in a tunnel oven operating at around 160 degrees Celsius. Each finished pack receives an inkjet-printed date code and batch number from a variable data printer. The printer adjusts to the motion of the conveyor, ensuring clear marking without interrupting product flow. Packaged products are conveyed to palletizing stations. Robotic palletizers, equipped with vacuum or mechanical grippers, stack trays in precise layer patterns onto standard pallets. Slip sheets may be inserted between layers for stability. Full pallets are wrapped using a rotary arm stretch wrapper. The film roll is tensioned to apply a tight wrap without deforming the boxes. Wrapped pallets are transferred to refrigerated holding or shipping docks for distribution. Throughout the process, programmable logic controllers synchronize machine timing, belt speeds, pump volumes, and thermal settings. Human-machine interface panels monitor all parameters and log production data. The entire line is modular and scalable, allowing simultaneous production of multiple donut types. Conveyors interlink each station, minimizing manual transfer and optimizing flow. Changes in donut type or size are handled through automated tool change, systems, or quick swap components. Pre-programmed recipes stored in the central control system reconfigure the line settings within minutes. Staging silos and ingredient feeders are equipped with load cells to precisely meter dry ingredients. Liquid ingredients are stored in jacketed stainless steel tanks with inline agitators to prevent settling or stratification. The dry and liquid ingredient streams merge at the mixer's inlet via butterfly valves controlled by digital weigh scales. The dosing accuracy ensures batch-to-batch uniformity, critical for dough performance during proofing and frying. Proofing chambers are equipped with belt elevation systems that loop the dough pieces through multiple horizontal levels. Fans and humidifiers ensure even air distribution, and digital probes record temperature and humidity in real time. Fryers are segmented into temperature zones with independent heating coils managed by thermocouple feedback. This zoning ensures even coloring across all donut types, regardless of fill or topping. Oil levels are maintained by float-based control valves, and inline filtration runs continuously. Spent oil is periodically replaced using external storage tanks connected by insulated pipelines and pneumatic pumps. The icing station includes a recirculation tank and a filtration mesh that removes solid particles from reused icing. Viscosity is measured using a rotational viscometer integrated into the circulation loop. Decorative elements such as drizzle patterns or text are applied using programmable depositor heads, which trace patterns based on CAD instructions and synchronize with conveyor speed to ensure alignment. Filled donuts pass through an X-ray inspection tunnel, identifying underfilled or foreign material contaminated units. Rejected items are diverted to a side conveyor for manual review. donuts for seasonal assortments are coded with quick response QR markers beneath their trays, allowing downstream distribution centers to sort mixed lots via machine vision systems and RFID tracking. Dunkin' Donuts. Donut production begins with dry ingredient blending, high-protein wheat flour, dextrose, sugar, soy flour, non-fat milk powder, salt, dough conditioners, and chemical leavening agents such as sodium bicarbonate and monocalcium phosphate are measured by weight and transferred into large-capacity industrial mixers using pneumatic conveying systems or gravity-fed hoppers. Liquid ingredients, including water, liquid shortening, and egg yolk solids, are preheated and pumped into the mixer via metered dosing systems. Water temperature is held between 27 to 30 degrees Celsius to activate gluten formation without overheating. Mixers equipped with high-torque planetary paddles operate in timed cycles to combine the dough, typically lasting 8 to 12 minutes. Dough temperature is monitored continuously with inline probes. Target final dough temperature is around 27 degrees Celsius for yeast-raised donuts to ensure optimal proofing behavior. Once mixed, the dough is transferred to a resting trough conveyor for gluten relaxation and hydration equilibrium, allowing for consistent sheeting performance. The rested dough moves to a multi-stage sheeting system composed of compression rollers that gradually reduce thickness in incremental stages. Roller gap adjustments are motorized and recipe controlled. Final sheet thickness is typically 9-11 millimeters, depending on the donut style. A light dusting system applies fine cornstarch or rice flour across the dough sheet surface to prevent sticking. The sheet then feeds into a rotary die cutter system. The cutter contains interchangeable dies for different donut varieties, including ring shapes, filled rounds, bars, and novelty shapes. The cutting drum rotates in synchronization with the conveyor to ensure clean, high-speed cuts. Cut donuts are transferred onto wire mesh proofing trays by vacuum-assisted pick-and-place systems. The trays are automatically stacked into a multi-tiered conveyor rack that moves through a temperature and humidity-controlled proofing chamber. Proofing conditions are held at 38 to 40 degrees Celsius, with 80-85% relative humidity for 35 and 45 minutes. Within the proofer, dough pieces rise and expand due to yeast activity. Conveyor motion is timed so that each tray spends the same duration in the chamber. Sensors track fermentation progression using size and weight benchmarks. After proofing, trays enter an automated unloading system that transfers the dough pieces onto a fryer in-feed belt. Frying oil is a refined, high-stability vegetable shortening maintained at 185-190 degrees C. The fryer contains a dual-zone heating configuration and a submersion system using paddle arms that guide and flip the donuts midway through frying. Total fry time is approximately 90 seconds. Ring donuts are flipped automatically after 45 seconds by rotating bars. Filled donut bases remain face up to maintain a flat bottom. Oil turnover is managed through continuous filtration using a centrifugal separation system and micron-level mechanical filters to remove particulates. As the donuts exit the fryer, excess oil is removed by angled mesh belts and compressed air nozzles. Products then travel along a cooling conveyor system with ambient airflow, reducing surface temperature below 35 degrees Celsius before handling. Ring donuts destined for glazing pass under a waterfall-style glazing station. The glazing tank contains a high-shear mixer that maintains solution homogeneity. A recirculating pump delivers glaze to a curtain nozzle that flows over the donuts. Excess glaze drains back into the holding tank through a mesh screen. Filled donuts proceed to a pressurized injection system. Each donut aligns with a dual or quad nozzle filler head that penetrates the side or bottom. Piston pumps dispense fillings such as jelly, cream, or custard with precision-controlled volume, typically 18 to 25 grams per unit. After filling, donuts requiring icing are transferred to a top-down depositor. This system uses heated reservoirs that keep icings at 40 to 45 degrees Celsius. Servo-controlled valves open and close based on donut presence detected by photoelectric sensors. Depositor heads apply a measured layer of icing across the top surface. For varieties requiring toppings, donuts travel under a vibratory topping applicator. Toppings such as chopped peanuts, sprinkles, or coconut shavings are dispensed via a rotating auger or oscillating tray, which evenly distributes material across the icing surface. Adhesion is achieved by timing the topping deposit immediately after icing application. Powder-coated or sugar-rolled donuts are conveyed into a rotating tumbler drum. A controlled feed of granulated or powdered sugar enters through a dosing hopper. The drum rotates at a calibrated RPM to coat donuts uniformly without damaging their structure. Fine mesh filters remove sugar clumps from the recirculation stream. Donuts with drizzle designs undergo a separate decoration process using linear motion gantry arms. These arms carry nozzles that deposit thin lines of icing, chocolate, or flavored syrup in programmed patterns. Motion control algorithms synchronize nozzle movement with conveyor speed for accurate designs. Post-decoration, all donuts pass through a spiral cooling tower. This vertically stacked conveyor system allows compact, high-capacity cooling with continuous airflow. Residence time is typically 15 to 20 minutes, allowing toppings to set and fillings to stabilize. Donuts exit the spiral cooler and enter a high-speed vision inspection system. Industrial cameras mounted above and to the side scan each product. Parameters such as size, color, symmetry, icing coverage, and fill injection marks are analyzed in real time. Out-of-spec items are removed via air-jet ejection systems. Acceptable donuts are organized into lanes using servo-driven diverter arms. Grouping is based on variety and pack size. Collation belts accumulate donuts into patterns that match tray cavities. Packaging begins with automatic tray erecting. Flat paperboard blanks are fed into a forming unit that applies glue and folds trays into shape. Form trays move beneath pick-and-place units with vacuum suction cups that deposit donuts into each cavity. Assorted variety packs are assembled by robotic gantries with product recognition software. These systems pull donuts from buffer conveyors and place them according to pre-programmed variety maps. Tray sealing depends on the product format. Some are closed with plastic lids, applied and snapped into place by mechanical presses. Others use film sealing units with heated jaws that apply plastic film over the tray and bond it along the edges. Package trays are labeled using thermal inkjet printers. Labels include production codes, variety, and timing information. Alignment sensors ensure accurate label placement without interrupting conveyor flow. Trays are loaded into cardboard master cases using side loading systems. Collapsible cases are automatically erected from flat blanks and fed into the loading station. Case flaps are glued and sealed using hot melt adhesive heads. Filled master cases are conveyed to a robotic palletizer. A vision-guided robot stacks cases in alternating patterns for load stability. Slip sheets are added at programmed intervals to separate layers. The stack height is optimized for transport requirements. Each completed pallet is wrapped with stretch film using a rotary arm wrapper. The arm spins around the stationary pallet, tensioning the film for secure transport. Film overlap and wrap count are controlled digitally to match load size. Wrapped pallets are labeled with barcoded identification tags applied by robotic labelers. Pallets then enter a gravity-fed conveyor line toward refrigerated loading docks or cold storage. Throughout the production line, operations are governed by a distributed control system. Programmable logic controllers handle station-level automation, while supervisory control and data acquisition systems log all machine parameters, production metrics, and alarms. Recipe management software controls all batch-dependent variables, including mixing time, proofing duration, fryer temperature, fill weights, and topping dosages. Each donut type has a profile stored in the system, allowing for rapid product changeovers with minimal downtime. Dry ingredient silos are equipped with level sensors and load cells. Refilling is coordinated with automated delivery systems to ensure continuous availability. Ingredient dosing systems operate under gravimetric and volumetric control for precise formulation. Liquid shortening is held in insulated tanks with inline heaters and agitators to maintain uniform viscosity. Delivery lines are jacketed and circulate hot water to prevent solidification. Pumps use variable frequency drives to adjust flow rate based on batch requirements. Filling hoppers for creams and jellies are jacketed for temperature control and agitated to prevent phase separation. Fill viscosities are monitored using inline viscometers, and pressure is regulated to prevent overfill or underfill. Proofing conveyor belts are made from non-stick, food-grade materials and guided on multiple horizontal tiers. Air circulation is forced through dampers to ensure uniform proofing across all trays. Temperature and humidity are logged for each cycle. Fryer systems include zoned heating elements and oil curtain barriers to minimize heat loss. Oil flow rate and turnover frequency are tracked by volumetric flow meters and recirculation pumps. Air knives at the fryer exit are powered by centrifugal blowers with adjustable nozzles. Their position and pressure are calibrated to strip excess oil without disturbing surface structure or toppings. Glazing tanks are cleaned and refilled on a timed schedule using CIP circuits. Glaze viscosity is maintained with real-time temperature feedback loops and monitored by rotational viscometers. All conveyors, transfer points, and topping stations are modular and mounted on quick-release brackets, allowing reconfiguration for new product lines or seasonal variations. The manufacturing process for Chips Ahoy! Cookies begins with precise dry ingredient batching. Key components include enriched wheat flour, sugar, brown sugar, baking soda, salt, and emulsifiers. These dry ingredients are stored in silos or super sacks and automatically dispensed via auger-fed feeders into high-capacity weigh hoppers. Load cells measure each ingredient to exact tolerances before being discharged into the mixing system. In parallel, liquid ingredients are prepared. These include water, high fructose corn syrup, molasses, glycerin, and vanilla flavoring. Liquid fats such as palm or soybean oil are stored in heated, jacketed tanks and pumped through insulated lines to maintain target viscosity. Liquid dosing is controlled using flow meters and metered pumps integrated into the batch control system. All ingredients are conveyed to an automated horizontal batch mixer. The mixing cycle follows a strict sequence: creaming of fats and sugars first, followed by the introduction of liquid components, then gradual incorporation of dry flour-based ingredients. Mixing speed and time are controlled by PLCs based on the dough formulation. Dough temperature is maintained between 20 ×4 to preserve texture consistency. Once the base dough is formed, chocolate chips are added. These are stored in climate-controlled hoppers to prevent melting or clumping and are added during the final low-speed mixing phase to avoid breakage. Chip loading is calibrated by weight to ensure uniform distribution across the batch. Mixed dough is discharged from the horizontal mixer into a dough handling system, which typically includes a feed conveyor and a rotary chunker. The chunker breaks large volumes into manageable portions for downstream processing. Dough portions are conveyed to the forming line. Portioned dough enters an extrusion-based depositor system. The depositor uses servo-controlled pistons to extrude dough through circular nozzles onto a moving oven band. Each cookie unit is dropped at exact intervals to maintain spacing and size. Depositor nozzles are non-stick coated and fitted with sensors to detect flow irregularities. The formed dough pieces move directly into a multi-zone continuous baking oven. The oven band is typically a steel mesh or solid band, depending on desired bottom texture. The oven is divided into several independently controlled thermal zones, with temperatures ranging from 180 degrees C to 230 degrees C. Baking duration is precisely set, typically between 6 to 10 minutes. As cookies move through the oven, moisture evaporates rapidly in the early zones, setting the outer structure. Later zones apply radiant and convection heat to develop interior texture and caramelization. Infrared sensors monitor surface temperature, and humidity sensors measure exhaust moisture for quality tracking. Exiting the oven, cookies pass onto a series of wire mesh cooling conveyors arranged in serpentine or spiral layouts. Ambient forced air circulates across multiple tiers to reduce cookie temperature from above 112 degrees to below 35 degrees within 8 to 12 minutes. Cooling speed is critical to avoid cracking or warping. Cooled cookies then enter a vision inspection system. High-speed cameras and image processing software detect dimensional conformity, color uniformity, chip distribution, and surface defects. Defective units are ejected via pneumatic actuators or diverter arms. Passing inspection, cookies are aligned into lanes via vibratory feeders and belt diverters. Lane alignment facilitates entry into the packaging system. Product counters track units per minute and signal robotic collators when batch quantities are ready. Packaging begins with slug loading. Cookies are grouped into vertical stacks, or horizontal slugs using indexing belts and pushers. Slug formation is synchronized with wrapper film feed using registration marks and encoder-driven rollers. Each cookie slug is pushed into a horizontal flow wrapper. Wrapping film is heat sealable and typically polypropylene based with a moisture barrier coating. The film unwinds from a roll and wraps around the cookie slug as it is propelled forward. Longitudinal and transverse heat sealers create the fin seal and end seals in rapid succession. Sealed packs exit the flow wrapper and pass under an inkjet coder that prints date codes and batch identification using edible grade ink. The print head operates in coordination with conveyor speed to maintain legibility. Wrapped packs are conveyed to cartoning machines. Here, cartons are formed from flat blanks by mechanical arms and glue stations. Wrapped slugs are side-loaded into open cartons, which are then closed, sealed, and printed with product and batch information. Cartons are grouped into shipping trays using automated case packers. These machines use robotic pick-and-place arms or pusher mechanisms to load cartons into corrugated cases. The case flaps are sealed using hot melt glue or tape applicators. Full cases move to a robotic palletizer station. Cases are arranged into a predetermined pallet pattern, layer by layer. Slip sheets may be added automatically between layers to improve load stability. Each layer is compressed slightly to ensure uniform height. Completed pallets are conveyed to a stretch wrapping station. A rotating arm or turntable applies plastic film under tension, with pre-stretch rollers ensuring optimal film usage and secure load containment. Wrapping cycles are adjusted for pallet height and weight. Each pallet receives a scannable barcode label printed by an industrial thermal printer. Labels are applied on two adjacent sides for redundancy. Pallet data is logged into the central warehouse system for tracking and inventory. Control. Ingredient replenishment is coordinated with automated inventory management. Raw material silos and liquid tanks are equipped with level sensors and integrated into the batch scheduling system. Ingredient usage is monitored in real time to prevent production interruptions. Throughout the production line, all mechanical systems are controlled by PLCs communicating through an industrial Ethernet network. Recipe parameters are stored in a central HMI interface, allowing operators to switch product types by loading preset programs. Mixing cycle parameters include motor torque, bowl rotation speed, and batch temperature. If values deviate from preset ranges, alarms are triggered, and production can be halted for correction. Chocolate chips are dispensed through vibratory feeders equipped with mass flow sensors. Feed rate is adjusted automatically to match dough throughput. Chips are gently folded into the dough using planetary paddles to preserve shape and prevent smearing. Extrusion depositors are cleaned and recalibrated between batches. Nozzle calibration uses laser measurement systems to verify uniform drop size across all channels. The baking oven includes thermal profiling tools, traveling temperature probes mounted on dummy cookies that measure time and temperature exposure across zones. These profiles are compared to standard references to ensure bake uniformity. Airflow in the cooling conveyor is managed by adjustable baffles and high-volume blowers. Zones are configured to prevent condensation or localized overheating, which could impact texture. Packaging film is spliced automatically using a festoon buffer system, allowing roll changes without stopping the wrapper. Splice detection sensors verify successful transfer and trigger rejection of the transition pack if required. Flow wrappers are equipped with film tracking systems using edge guide sensors to maintain alignment. Tension controllers manage unwind force to prevent film distortion. Cartoning machines feature vision systems that verify correct pack orientation before loading. Misoriented or missing packs trigger reject mechanisms that divert affected cartons to inspection lanes. Case packers use Delta-style robots with suction grippers or mechanical claws. Gripping pressure is adjustable to avoid crushing while maintaining speed. Robot arms operate on articulated joints with sub-millimeter precision. Palletizer systems incorporate automatic pallet dispensers and slip sheet feeders. Gripper heads are interchangeable for different case sizes and stacking formats. Production data, including line speed, output volume, defect rate, and downtime, is continuously recorded and transmitted to a manufacturing execution system. Reports are generated hourly for supervisory review and performance tracking. Temperature-sensitive ingredients, such as chocolate chips and syrup, are stored in climate-controlled zones. Delivery lines use nitrogen flushing or vacuum seals to prevent oxidation and contamination. Finished goods are staged in a climate-regulated buffer zone before loading. Inventory movement is tracked via RFID-tagged pallets, which interface with the logistics management software. This documentary dives inside the factories that turn corn and potatoes into Cheetos, Lay's, and Doritos crisps. From raw ingredients to massive mixers, seasoning drums, and precision packaging, the process moves at incredible speed with relentless efficiency. Let's reveal the machines and methods that shape each iconic crunch, showing how their flavors are engineered every single day. Cheetos are produced using a high-output, continuous extrusion system designed for the transformation of dry cornmeal into expanded puffed snacks through controlled heat, pressure, moisture, and mechanical shear. The raw material input begins with degermed cornmeal, which is stored in silos, connected directly to the process line through a network of pneumatic conveyors. The cornmeal is sifted through mesh screens to remove foreign particles, then passed through a dehumidifying chamber to achieve a standardized moisture content between 10.5 and 11.5% before entering the preconditioner. In the preconditioning chamber, dry cornmeal is mixed with water and steam under tightly regulated parameters. The purpose of preconditioning is to hydrate the meal to a target range of 18 to 20% moisture, while partially gelatinizing the starch to prepare it for the extrusion stage. The chamber uses dual shaft paddles rotating at independent speeds to ensure homogeneous hydration without introducing air pockets. Live steam is injected directly through precision steam valves with real-time moisture levels monitored using NIR, near-infrared, sensors, and inline conductivity probes. From the preconditioner, the moistened meal is transferred directly into the barrel of the extruder. The extruder is a twin screw or single screw configuration depending on the specific formulation, with segmented barrels for independent control of heating zones. Each zone of the extruder barrel is jacketed and fitted with thermocouples and pressure sensors. The screws inside the extruder rotate at speeds between 300 and 600 RPM and apply intense shear, mixing, and compression to the meal. As the material travels along the screw channel, the combination of mechanical energy and barrel heating increases the temperature of the dough to 140, 180 degrees, while the pressure rises to 1500 to 3000 psi. Under these conditions, the starch within the cornmeal fully gelatinizes and the protein matrix denatures, forming a viscous melt that is cohesive and plastic in behavior. At the final die plate, the pressurized melt exits into atmospheric pressure, causing rapid vaporization of internal moisture. This sudden expansion creates the puffed structure of the Cheeto. The die shape is critical for the form factor of the snack. For classic crunchy Cheetos, the die orifice is a small circular hole, and the dough extrudes as a continuous rope. A rotating knife positioned at the exit face of the die cuts the rope into short, irregular lengths at 200 and 400 cuts per minute, depending on the desired texture. The extruded pieces fall onto a vibrating conveyor belt that transports them into the frying system. For crunchy variants, the base extrudates are fried in a continuous oil bath system. The fryer is filled with vegetable oil, commonly corn or canola oil, maintained at 170 to 190 degrees Celsius, using heat exchangers and recirculation pumps. The extrudates enter on a submerged conveyor belt that keeps them fully immersed for 30 to 45 seconds. During this time, surface water evaporates, and the structure is locked in through rapid dehydration. Oil absorption is measured using inline sensors and confirmed by batch gravimetric analysis. After frying, the product is lifted out of the oil and passes through a cascade of air knives or centrifugal de-oiling drums to remove excess surface oil. The fried product is then conveyed through a multi-stage cooling tunnel where ambient or chilled air flows across vibrating trays to reduce product temperature to under 40 degrees Celsius before seasoning. Airflow is adjusted with dampers to maintain a uniform cooling gradient and avoid moisture migration. For puffed variants, the extrusion process differs at the post-extrusion stage. Instead of frying, the puffed extrudates are conveyed directly into a hot air dryer. The dryer operates at 120 to 160 degrees and includes multiple conveyor decks with perforated trays. Heated air is circulated through the product bed at controlled velocities and relative humidity. Residence time in the dryer ranges from 8 to 12 minutes, depending on piece size and moisture content at exit. Final moisture is targeted at 2 to 3% by weight. After drying or frying, Cheetos pieces are conveyed to the seasoning drum. This is a rotating cylindrical tumbler lined with helical flights to elevate and tumble the product uniformly. The base seasoning is stored in a hopper above the drum and dispensed through a vibratory feeder into a powder application system. Oil-based or water-based slurries are sprayed through atomizing nozzles onto the surface of the snacks as they rotate inside the drum. The seasoning adheres to the surface oil or residual moisture, forming a uniform coating. The slurry composition includes cheese powder, salt, flavor enhancers, colorants, and anti-caking agents. Slurry viscosity is controlled through inline viscometers, and pump speed is adjusted accordingly. Spray coverage is monitored using camera-based imaging systems that detect color uniformity across product samples. Seasoning overuse or underuse is automatically corrected by adjusting feeder rates or nozzle flow. Seasoned snacks are passed through a final cooling stage to ensure surface dryness and coating fixation. Cooled air is circulated over a vibratory conveyor bed, and product temperature is lowered to under 30 °C. The flow rate and cooling length are calibrated to prevent clumping in the packaging stage. Once cooled, the product is conveyed to the weighing and bagging station. Multi-head combination weighers are used to portion the product into precise fill weights, typically between 15 and 300 grams, depending on bag size. Each head drops a known quantity into a central chute when the calculated sum matches the target fill weight. The portioned product is dispensed into pre-formed bags or into a form-fill-seal machine. The vertical form-fill-seal system uses film rolls printed with product branding. The film is fed through a forming collar, sealed longitudinally, and then sealed at the top and bottom to create a pillow pouch. The filled bags pass through a check weigher and metal detector. Packages outside the weight tolerance or those triggering metal detection are automatically ejected via pneumatic arms. Conforming bags are grouped and conveyed to case packing robots. Robotic arms, equipped with vacuum grippers or mechanical paddles, load bags into pre-erected cartons or display-ready trays. Cartons are closed using hot melt adhesive and labeled with product code, batch number, and expiration date, using print and apply labelers. Finished cartons are then conveyed to the palletizer. Palletizing robots stack cartons onto wooden or plastic pallets according to a programmed pattern. Each layer is compressed to improve load stability, and the full pallet is stretch wrapped using a rotary arm wrapper. The pallet is labeled with an SSCC code and barcode linked to the manufacturing execution system. Pallets are transferred to the warehouse and stored under controlled humidity and temperature until distribution. Throughout the process, every production parameter is monitored and logged by a centralized SCADA system. Extruder temperature, pressure, die configuration, screw speed, moisture content, oil temperature, seasoning flow, and packaging weight are all tracked in real time. Automated alerts notify operators of deviations outside process limits. Batch data is stored and used for traceability, yield calculation, and process optimization. Lay's production begins with the intake of bulk potatoes delivered by truck or conveyor into receiving hoppers. Potatoes are unloaded into flume systems filled with recirculating water, which use hydraulic movement to carry them to the first stage of processing. This flume system not only transports the potatoes, but also initiates pre-washing to remove surface soil and debris. Upon exiting the flume, the potatoes enter a rotating drum washer fitted with abrasive surfaces and high-pressure spray nozzles. This drum rotates slowly while jets of water dislodge residual dirt from the potato surface. The wash cycle time is optimized to avoid damaging the skin while ensuring that every tuber is completely clean. The cleaned potatoes are then conveyed to an inspection belt, where optical sorting systems equipped with high-resolution cameras scan for defects such as green skin, rot, or deformities. Non-conforming potatoes are removed by targeted air jets activated in milliseconds. Accepted potatoes are then directed to the peeling stage. Mechanical peelers utilize either steam pressure or abrasive rollers. In steam peeling, potatoes are exposed to high-pressure steam in a sealed vessel for a few seconds, then rapidly released into a vacuum chamber, causing the skin to rupture and loosen. The loosened skin is removed with soft brushes and water sprays. In abrasive peeling, the tubers are rotated inside a drum lined with abrasive surfaces that scrape the skin off while minimizing flesh loss. After peeling, potatoes are rinsed again to remove any residual skin particles. Peeled potatoes are conveyed via stainless steel belts to slicing machines. These are centrifugal slicers equipped with rotating impellers that force each potato against razor-sharp blades mounted on a rotating head. Blade thickness is adjustable down to tenths of a millimeter to produce slices typically between 1.2 and 1.5 millimeter thick. The speed of both the impeller and cutting head is synchronized to maintain consistent thickness regardless of potato size. Slices exit the cutter in a continuous stream and are immediately passed through a water flume to prevent browning caused by enzymatic oxidation. The sliced potatoes are then subjected to blanching. This step involves immersion in hot water or passage through a hot water curtain at 65 to 75 degrees Celsius for 1 to 2 minutes. Blanching reduces starch levels on the surface of the slices, which is necessary for achieving uniform golden color and reducing sugar-related dark spots during frying. It also partially gelatinizes surface starch, which influences final texture. After blanching, the slices are rinsed with cold water and passed over dewatering screens or air knives that remove excess moisture before frying. Next, the slices enter the continuous frying system. The fryer consists of a stainless steel trough filled with vegetable oil, maintained at a temperature between 170 and 190 degrees Celsius, using external heat exchangers and recirculating pumps. The oil is filtered continuously using inline centrifugal or bag filtration systems to remove fines and prevent degradation. Slices are carried through the fryer on a submersion belt that ensures each one is fully immersed for a specific dwell time, usually between 2 and 3 minutes. The exact time and temperature profile is controlled by SCADA systems to produce chips with consistent moisture content below 2%. As the chips exit the fryer, they pass through an oil removal system consisting of vibrating conveyors and high-velocity air blowers or centrifugal de-oiling drums. These reduce surface oil, improving shelf life and texture consistency. The chips are immediately cooled by ambient or chilled air using tunnel coolers that bring the product temperature down below 40 degrees Celsius within 90 seconds. This cooling step also halts cooking and stabilizes texture. After cooling, the chips enter the seasoning system. A vibratory conveyor feeds them into a rotating drum lined with helical flights to provide continuous tumbling. Liquid or powder seasoning is applied via spray bars or auger-fed dosing units mounted above the drum. Liquid flavor systems use oil-based carriers with atomizing nozzles to create fine, even coverage. Powder seasonings are dosed based on real-time weight feedback to maintain precise seasoning ratios. The tumbling action ensures uniform adhesion of the seasoning to the chip surface. From the seasoning drum, chips are transferred via vibrating or belt conveyors to the packaging area. Along the way, they pass through optical inspection systems that detect burnt or misshaped chips using near-infrared cameras and remove them using targeted compressed air pulses. Chips then fall into the radial combination weigher, which consists of multiple buckets that each dispense a known quantity. A computer selects the optimal combination of buckets to match the target fill weight with high accuracy, typically within plus 0.1 grams. Portioned chips are released into the forming tube of a vertical form fill seal machine. Here, pre-printed film is formed into a tube, sealed longitudinally and sealed at the bottom to form a pouch. The chips are dropped in, and the top is sealed to complete the package. The seal jaws also cut the film to separate each bag. Each package passes through a check weigher to verify total mass and a metal detector to ensure food safety. Out-of-spec packages are automatically ejected onto a rejection lane. Accepted packages move to high-speed collation and case packing systems. Multiple bags are grouped together using timing belts and dropped into pre-formed cartons or display trays. Automated case sealers close and glue the boxes. A print and apply labeler affixes tracking labels with batch number, expiration date, and barcode. Cartons are conveyed to a robotic palletizer that stacks them according to pre-programmed pallet patterns, optimizing space and transport efficiency. Full pallets are wrapped in stretch film using a rotary arm or turntable wrapper. A barcode, label with product and pallet ID is applied. Pallets are transferred to a climate-controlled warehouse held at consistent temperature and humidity to preserve texture and prevent oil oxidation. All product data, including ingredient lot numbers, frying oil batch, line performance data, and packaging codes are stored in the plant's MES database for full traceability. Throughout the process, ingredient inputs, machine speeds, temperatures, moisture levels, oil quality, and product weights are monitored in real time by integrated control systems. Operators interface with the process through HMI panels, which display alarms, trends, and machine statuses. Recipes are stored digitally and selected at line start to automatically load all relevant parameters across slicing, frying, seasoning, and packaging modules. Cleaning between flavor changeovers involves flushing, slicing, and seasoning systems, draining and filtering oil as needed, and changing packaging film rolls. Flavor specific. Residue is minimized through modular drum systems that can be swapped out quickly and cleaned offline. Line efficiency and waste percentages are recorded for each run and reviewed during shift changeover meetings for continuous improvement. A high-capacity Lay's line is capable of producing between 10 and 15 tons of finished chips per hour, depending on chip type, size, and flavor. Lines can operate for up to 20 hours per day with planned cleaning and maintenance windows. Raw potato usage, slicing yield, oil usage, seasoning consumption, and finished product throughput are tracked and analyzed daily for operational optimization. Doritos are produced using a continuous process that begins with raw corn as the base input. The corn arrives in bulk and is stored in vertical silos with aeration systems to maintain stable moisture content. Each batch is gravity-fed into a cleaning system where the kernels pass through vibrating screens, destiners, and aspiration channels to remove dust, stones, and foreign matter. Magnet separators extract any ferrous contaminants before the corn enters the next stage. The cleaned corn is fed into a steeping tank or continuous cooker where it is exposed to water at temperatures between 80 and 100 °C. The corn remains in this system for 30 to 45 minutes, depending on its initial hardness and desired hydration level. Water is continuously circulated and filtered to remove loosened pericarp, and the corn's internal moisture content rises to around 40 to 45%. Cooked corn is discharged onto dewatering screens and conveyed to the stone mill. The stone mill grinds the wet corn into masa, a soft, pliable dough. The grinding mechanism consists of two rotating stones, one fixed and one rotating, with adjustable spacing to control grind texture. The heat and friction from grinding partially gelatinize the starch. The resulting masa is collected in a trough and transported via auger to the sheeting system. No preservatives or additives are introduced at this stage. Masa is fed into a sheeter system consisting of dual rollers, calibrated to produce a uniform sheet of dough at a thickness between 1.2 and 1.5 millimeters. The sheet is continuously monitored using laser micrometers that provide real-time feedback to the roller gap actuators. The dough sheet moves onto a die-cutting system where rotary cutters stamp out the triangle shape of each Dorito. Scrap masa is collected and returned to the auger to be reblended into fresh dough within a defined recycle ratio. Cut chips move on a perforated conveyor where they are lightly dusted with corn flour to prevent sticking, and then enter a 3-zone oven. The oven zones are independently controlled for temperature and airflow. The chips are partially baked at 300 to 400 degrees over a total residence time of 45 to 60 seconds. This reduces surface moisture and creates a semi-rigid structure suitable for frying. The internal moisture content is reduced to around 20% by weight. Partially baked chips exit the oven and are transferred via vibratory conveyors to the continuous fryer. The fryer is filled with high oleic vegetable oil, typically corn or sunflower oil, filtered and recirculated through plate filters to maintain clarity and reduce polar compound formation. Oil temperature is held at 180 to 190 degrees Celsius. Chips enter on a submersion belt and are fried for 50 to 90 seconds, depending on their moisture content and thickness. During frying, final moisture is reduced to less than 2%, and texture is developed through rapid dehydration and surface expansion. Upon exiting the fryer, the chips pass through an oil removal stage. This includes air knives and optionally a centrifugal de-oiling system that rotates baskets at up to 1000 RPM to spin off residual oil. After de-oiling, the chips enter a cooling conveyor system where ambient or chilled air flows across a vibrating bed to bring product temperature below 40 degrees Celsius in under 2 minutes. The cooled chips are then routed into the seasoning drum. This is a horizontal, cylindrical tumbler fitted with internal flights that lift and rotate the chips as they pass through. Seasoning application occurs via two systems: dry powder feeders and liquid slurry sprayers. The dry powder feeder consists of a vibratory tray with variable speed auger dispensing seasoning mix at a calibrated rate. Liquid slurries containing oil-based flavor carriers are sprayed using pressure nozzles fed by gear pumps. Flow rates are adjusted in real time based on chip throughput measured by load cells at the drum's infeed. Seasoning distribution is monitored using optical cameras and hyperspectral imaging to evaluate surface coverage and color uniformity. If discrepancies are detected, feed rates are adjusted automatically. Once seasoned, the chips are conveyed to the packaging section. En route, they pass through inspection systems that identify and reject burnt or broken chips using high-speed cameras and targeted air jets. The accepted chips are transferred to multi-head combination weighers. These weighers consist of multiple hoppers, each holding a portion of chips. A computer algorithm selects the combination of hoppers that adds up closest to the target package weight with minimal deviation. The selected portions are released into a form, fill, seal machine. The packaging film is unwound from rolls and guided through a forming collar, where it is shaped into a tube. The back edge is sealed with a vertical heat sealer, and bottom and top seals are created by horizontal jaws synchronized with the drop of each portion of chips. Packages are filled, sealed, and separated continuously. Each bag passes through a check weigher and metal detector. Non-compliant bags are ejected automatically. Bags are transported to the collation area where they are grouped into sets for case packing. Robotic arms equipped with suction cups pick multiple bags at once and place them into preformed cartons. Cartons are closed using hot melt adhesive applied by precision nozzles and sealed under pressure. Each box is labeled with batch number, expiration date, and a scannable barcode. Cartons are transferred to palletizing cells. Industrial robots, equipped with vacuum grippers or mechanical paddles, stack cartons in a predetermined pattern onto wooden pallets. Full pallets are wrapped using stretch film applied by a rotating arm or turntable system. A final barcode is applied to each pallet for inventory tracking and scanned into the warehouse management system. Pallets are stored in climate-controlled distribution warehouses maintained at target humidity levels to prevent chip degradation. All critical production data, including ingredient batch numbers, processing parameters, oil usage, seasoning data, packaging film codes, and output weights, are logged automatically by the SCADA system. This data is linked to the finished product batch code and can be retrieved for quality, control, traceability, and efficiency analysis. Flavor changes on the production line require equipment cleaning, seasoning drum swap, packaging film change, and system flush. A changeover process is executed based on preloaded digital recipes that configure roller settings, fryer dwell times, seasoning flow rates, and packaging parameters. Downtime for changeovers is minimized using quick-release parts and automated washdown stations. Production lines are modular and scalable. A high-capacity Doritos line can produce between 3 and 7 tons of finished chips per hour, depending on product format. Processing yield is calculated based on raw corn input, fryer oil usage, and seasoning weight compared to bagged product output. Efficiency metrics such as frying oil turnover rate, seasoning coverage variance, and bag fill accuracy are continuously monitored and used for process improvement. Oil management is critical in Doritos production. Fryer oil is circulated through external heat, exchangers, and filtration units that remove carbonized particles and maintain oil quality. Oil is replenished continuously and measured using inline oil meters. Oil turnover is tracked to prevent degradation, which can affect flavor, shelf life, and texture. Used oil is discharged in controlled quantities and either recycled or disposed of based on operational protocols. Seasoning systems support multiple recipe profiles. Each recipe includes component percentages, feed rates, viscosity targets for slurries, spray nozzle pressures, and pump speeds. Recipes are stored digitally and loaded via the line's control interface. Seasoning is prepared in parallel tanks to reduce downtime between batches and allow flavor sequencing. Packaging lines operate at speeds between 60 and 150 bags per minute, depending on bag size and configuration. Packaging materials are stored in automated reels with sensors that alert operators when a roll change is needed. Packaging seal integrity is tested using vacuum or burst testing at specified intervals. Seal strength and print registration are logged alongside product weight and metal detection data. Each Doritos variant, whether original, spicy, lime-flavored, or limited edition, follows the same general processing flow, with adjustments made at the seasoning and packaging stages. The ability to scale and shift recipes allows the production line to handle dozens of flavor profiles without hardware changes beyond seasoning and film adjustments. Dr. Pepper production begins with water purification. Incoming municipal water is first passed through a series of coarse filters to remove sediment and particulates. It then flows into a multi-stage filtration system, including activated carbon beds that strip away chlorine, organic compounds, and any residual taste or odor. The water is then softened through ion exchange columns that extract calcium and magnesium. Finally, the water passes through reverse osmosis membranes operating at high pressure, forcing the liquid through semi-permeable membranes that eliminate dissolved solids, heavy metals, and microorganisms. The purified water is collected in stainless steel holding tanks, agitated continuously to maintain consistency and prevent stagnation. Concurrently, concentrated syrup production begins. This involves a precise blend of liquid sweeteners, flavor concentrates, acidulants, and coloring agents. High fructose corn syrup or liquid sugar arrives in tanker trucks and is pumped directly into insulated storage silos. From there, metering pumps draw exact amounts of sweetener into stainless steel mixing vessels. Each vessel is jacketed for temperature control and fitted with high-speed impellers. Flavor compounds are stored in temperature-regulated vats and dispensed in minute quantities using servo-controlled dosing systems. Each component is added in a fixed sequence to ensure homogenization and prevent chemical interaction before full dilution. Citric and phosphoric acid are added next via automated dosing units, lowering the pH and adjusting taste profile. Caramel color is injected through pressurized nozzles in measured bursts, darkening the mixture. After all ingredients are blended, the syrup passes through a plate heat exchanger for flash pasteurization. Heated to above 85 degrees Celsius for under 30 seconds, the syrup is then rapidly cooled to preserve flavor integrity. The syrup is piped into chilled storage tanks, each lined with food-grade epoxy to prevent contamination. These tanks are agitated at controlled RPMs to keep the syrup uniform. From this point, the syrup is mixed with the purified water. This occurs inside a continuous blending unit known as a proportioner. The unit draws both syrup and water in a 1:5 ratio using synchronized flow meters and magnetically actuated valves. Flow rates are adjusted dynamically based on inline refractometers that monitor sugar concentration in real time. Any deviation from target Brix level results in automatic recalibration of fluid inputs. The mixture then enters a deaeration chamber where it is subjected to vacuum pressure to remove entrained oxygen and carbon dioxide, which can affect taste and carbonation efficiency. Following deaeration, the liquid enters a carbonator. Inside a sealed stainless steel vessel, the beverage is chilled to near freezing temperatures to increase gas solubility. Liquid carbon dioxide is injected into the drink through a diffuser plate with thousands of microperforations. The gas dissolves rapidly under high pressure, saturating the beverage with carbonation. Rotary carbon pumps recirculate the liquid within the chamber to ensure uniform CO2 distribution. Carbonation levels are continuously monitored by inline gas volume analyzers. The carbonated beverage is held in pressurized buffer tanks awaiting transfer to the filling line. The filling process begins with bottle or can preparation. Empty containers arrive via conveyor belts in nested stacks or crates. A depalletizer equipped with vacuum grippers lifts layers of containers and places them onto the in-feed conveyor. Containers proceed through a rinser unit that inverts each one and blasts filtered air or sterile water inside to dislodge debris. The containers are then uprighted and transferred to the filler carousel. The filling machine features multiple heads, typically between 40 to 120, arranged in a rotary configuration. Each head is fed from the pressurized carbonated beverage tank. As a container aligns with a filling head, it is clamped and sealed. Counterpressure is applied to prevent foaming. A filling valve opens and the product is gravity-fed or gently pumped in. As the container fills, vent tubes displace internal gas to maintain pressure equilibrium. Once full, the valve closes and the container is released. Immediately after filling, containers proceed to the capping station. In bottle lines, caps are sorted and oriented using centrifugal feeders. Each cap is dropped into position and pressed onto the bottle using pneumatic or servo-controlled spindles. Torque sensors ensure proper seal strength. For cans, lids are fed through chutes and placed atop the can mouth. A seaming head engages, folding and curling the lid's edge around the can's rim to create a hermetic seal. The container is then released to a discharge conveyor. Sealed containers pass through an inline quality control system. High-speed vision sensors inspect each container for correct fill height, cap application, label alignment, and structural integrity. Any defective item is ejected via air-jet nozzles. Simultaneously, select containers are diverted for destructive testing. These include pressure retention tests, carbonation level checks using digital pierce testers, and torque measurements for closure tightness. Approved containers proceed to labeling. Bottles pass through a label applicator fitted with servo-driven rollers. Pre-printed labels on adhesive rolls are cut and transferred using vacuum drums. Each label is wrapped and smoothed onto the bottle's surface using motorized brushes. Can lines use shrink sleeve applicators? Sleeves are dropped over the cans and pass through a heat tunnel where forced air heaters contract the film around the container body with uniform tension. Each labeled item is scanned by barcode readers to verify correct SKU association. Labeled products travel to the packaging area. Containers are grouped into multi-packs using high-speed collators. For bottles, robotic arms or pneumatic sweepers push groups of 6, 12, or 24 into cardboard carriers or plastic overwrap. For cans, shrink film machines envelop the groupings with polyethylene film. The packs pass through shrink tunnels where the film tightens around the cans. Heat is applied via convection blowers at calibrated temperatures to avoid deformation. Finished multi-packs are conveyed toward case packing stations. Corrugated cartons are erected from flat blanks by automated formers and transported via belt to loading stations. Pneumatic. Pushers slide each multi-pack into its case. In robotic systems, Delta robots or articulated arms equipped with suction grippers lift and place products with extreme precision, adjusting in real time for orientation variances detected by machine vision. Loaded cartons proceed to automatic tapers that seal the top flaps with pressure-sensitive adhesive tape or hot melt glue. Sealed cases continue to the palletizing area. Pallet dispensers drop wooden or plastic pallets onto powered rollers. A layer building system positions cases in pre-programmed patterns for structural stability. Robotic arms or gantry-style palletizers pick cases and place them in rows, adjusting height via vertical actuators. Each layer may be interleaved with a slip sheet for added stability. Once a pallet is complete, a wrapping station envelops it in stretch film. The turntable spins while a vertical arm applies film under tension, binding the load tightly. The process for Sprite begins with the transformation of municipal water into beverage-grade base water. This water enters through insulated pipelines and is immediately routed into a sequence of stainless steel treatment vessels. First, it flows through a coarse mechanical screen to eliminate large particles. It then enters a pressurized sand filtration unit filled with graded quartz media, where finer solids are trapped. After this, the water moves into an activated carbon filtration chamber. Here, as it passes through beds of carbon granules, residual chlorine, organic molecules, and off odors are removed through adsorption. Next, the water is softened in a dual-tank ion exchange system. Calcium and magnesium ions are replaced with sodium ions to prevent mineral buildup in downstream equipment. From there, it proceeds into a reverse osmosis module, which uses pressure-driven membrane filtration to remove dissolved salts, nitrates, and bacteria. The output is ultra-clean water with consistent properties. Before storage, it is exposed to ultraviolet irradiation and passed through a 0.2 micron sterile filter to eliminate any remaining microbes. The treated water is directed into large, sealed stainless steel tanks fitted with slow-turning paddles that keep the fluid agitated and uniform in composition. Meanwhile, the flavor syrup is prepared in a separate, climate-controlled mixing room. The process begins by transferring liquid sweeteners, either high fructose corn syrup or refined liquid sucrose, from bulk storage tanks into jacketed blending vessels. These vessels are equipped with load cells to ensure exact quantities are used. Agitators start spinning to ensure even distribution. Into these vessels, concentrated flavor ingredients are injected using computer-controlled microdosing pumps. These include lemon-lime oil emulsions, natural citrus flavor distillates, and bitterness balancers. Citric acid is added as the key acidulant to provide Sprite's distinct tart profile. Sodium citrate is introduced to regulate the beverage's buffering capacity and stabilize acidity. Small quantities of preservatives are introduced last. The mixture is kept under continuous motion with variable speed impellers that prevent stratification. Once all components are incorporated, the syrup is heated rapidly in a tubular heat exchanger, held at pasteurization temperature for a brief duration, and then chilled through a countercurrent cooling system. Once cooled, the syrup is passed through a sterile filter and stored in closed-loop storage tanks under positive nitrogen pressure to prevent contamination. The next phase is inline blending. In this stage, the finished syrup is metered into a continuous stream of purified water. The blending takes place inside a high-precision mixing manifold, where magnetic flow meters monitor the real-time ratio of syrup to water. Proportional integral derivative controllers adjust valve positions automatically to maintain a consistent blend ratio. Inline refractometers provide Brix readings that validate sugar concentration. Once the beverage stream is formed, it moves into a deaeration tank where vacuum pumps lower the internal pressure to remove dissolved oxygen. This step is critical to improve carbonation absorption and prolong product stability. The deaerated mixture then flows into a cooling module that chills the liquid to near 0 graus Celsius using a glycol-based refrigeration loop. Lowering the temperature increases the solubility of carbon dioxide in the next step. Carbonation takes place in a pressurized tank equipped with high-efficiency diffusers. Liquid CO2 is injected under controlled pressure through stainless steel sparges that break the gas into fine microbubbles. As these bubbles rise through the cold beverage, the carbon dioxide dissolves into the liquid under saturation pressure. A circulation pump ensures the beverage continuously cycles through the carbonation chamber for uniform gas distribution. Inline gas volume analyzers measure the carbonation level in real time, while PID loops adjust CO2 flow rate and internal pressure accordingly. The carbonated product exits into a buffer tank held under constant pressure, ready for filling. Container preparation is a continuous process occurring in parallel. PET bottles or aluminum cans arrive from high-speed depalletizers that remove layers of empty containers using suction pads and robotic arms. The containers are placed onto conveyor belts and directed toward the rinsing system. For bottles, an inverted air rinse machine uses ionized air jets to dislodge any debris inside. Cans are washed with sterile water sprays and dried with compressed air. Once cleaned, the containers proceed toward the rotary filler. Filling occurs on a multi-head rotary machine where containers are positioned under filling valves arranged in a circular turret. The carbonated beverage is delivered from the pressurized buffer tank to the filler bowl. Each container is raised into position and sealed against a filling nozzle. First, the internal pressure of the container is equalized using a pre-evacuation chamber. Then, the valve opens and liquid flows in under gravity or slight overpressure. Vent tubes allow displaced gas to escape without disrupting carbonation. Once the container reaches its calibrated fill height, the valve closes and the container is lowered back onto the conveyor. Capping follows immediately. For bottles, caps are sorted and oriented using centrifugal feeders and fed into a rotary capper. Each cap is pressed onto the bottle and secured using torque-regulated chucks. Sensors verify cap presence and alignment. For cans, ends are placed on top by an end-feeding chute, and a seaming head curls the lid over the rim in a multi-stage process to form a hermetic seal. Once sealed, the containers pass through a pressurized water spray or vacuum chamber to remove any residual product from the exterior. The sealed containers move toward quality assurance. Systems. High-speed cameras check for correct fill levels, proper capping, and label placement. Infrared sensors detect internal pressure by analyzing surface deformation. Some containers are automatically diverted for destructive testing, including carbonation loss, torque verification, and microbiological sampling. Labeling varies by container type. For PET bottles, self-adhesive labels are applied using servo-driven applicators that wrap labels around the cylindrical surface. The applicator head synchronizes with container speed and uses rubberized rollers to press the label into place. In canning lines, shrink sleeves are applied over the containers, and the cans pass through a steam or infrared tunnel that contracts the film tightly around the can body. Optical sensors verify label presence, orientation, and print clarity. Labeled containers are grouped into multi-unit packages by a high-speed collation system. Bottles are mechanically pushed into plastic carriers or enclosed in cardboard sleeves using servo arms. Cans are collected into 6-packs or 12-packs and overwrapped in shrink film. The multi-packs then pass through a shrink tunnel where hot air circulates uniformly around the film, causing it to contract tightly without damaging the product inside. Packaged units are routed to case packing stations. Here, automatic erectors construct corrugated cases from flat blanks using glue or tape. Robotic loaders with vacuum end effectors pick up groups of bottles or cans and place them into the open cases in pre-programmed formations. The filled cases are sealed at the top using either hot melt adhesive applicators or pressure-sensitive tape dispensers. Cases proceed to palletization. Empty pallets are dispensed from a stack onto a conveyor. A layer-forming system organizes cases into a stable pattern using motorized guides and pusher arms. A robotic palletizer or gantry system transfers each layer onto the pallet, adjusting height and position after each pass. Between layers, slip sheets may be inserted to enhance stacking integrity. Once fully stacked, the pallet is moved into a stretch wrapping station. A rotating turntable spins the pallet while a film carriage moves vertically, wrapping the entire stack in tensioned polyethylene film to secure the load. The Canada Dry production process begins with the intake and treatment of raw water. Municipal water is directed into a series of pre-treatment systems through stainless steel pipelines. The first step is mechanical filtration, where water flows through mesh strainers that remove coarse particulates. Following this, it passes through a dual media sand and anthracite filtration system to eliminate finer suspended solids. The next stage is activated carbon filtration. As the water moves slowly through the carbon beds, chlorine, chloramine, and organic contaminants are removed through adsorption. The water is then softened using a sodium-based ion exchange system that exchanges calcium and magnesium ions for sodium ions, reducing scale formation in downstream equipment. After softening, the water is subjected to reverse osmosis using high-pressure pumps to force it through semi-permeable membranes that separate out dissolved solids, bacteria, and unwanted ions. The treated water then undergoes ultraviolet sterilization and sub-micron filtration to achieve microbiological purity before being transferred to agitated, sealed stainless steel storage tanks for use in the product blend. Parallel to this, the syrup production begins in a closed system syrup room. Liquid sweeteners, such as high fructose corn syrup, are delivered in heated tankers and pumped into bulk storage silos lined with food-grade coatings. These silos are equipped with volumetric flow meters and thermal controls. The sweetener is metered into stainless steel mixing vessels using precision dosing pumps. These vessels are jacketed for thermal regulation and include bottom-mounted mixers driven by variable frequency motors to achieve high shear mixing. Ginger extract, lime oil, lemon oil, and proprietary spice emulsions are stored in temperature-controlled dosing cabinets and delivered via sealed piping to the blending tanks. Dosage is governed by recipe management software, with peristaltic pumps calibrated for microdosing accuracy. Citric acid is introduced to provide tartness, followed by potassium sorbate or sodium benzoate as preservatives. Caramel color, if used, is injected through positive displacement pumps, controlled to a fraction of a milliliter per liter. Once all components are in the tank, the syrup undergoes a high shear mixing cycle. After homogenization, it is flash pasteurized by pumping through a plate heat exchanger system, reaching temperatures above 85 Stichtag for a few seconds, and then rapidly cooled using a countercurrent chilling loop. The syrup is passed through sterile filters and transferred into insulated holding tanks with nitrogen blankets to prevent oxidation and maintain flavor integrity. With syrup and water prepared, they are combined using an inline blending system. This unit uses magnetically driven flow meters to monitor real-time volumetric flow of each stream. PID-controlled valves adjust the ratio continuously to maintain the programmed syrup-to-water proportion. The blend passes through a series of mixing chambers where turbulence is created using static mixers to ensure full molecular integration. An inline refractometer measures the resulting brick's level, and adjustments are made automatically to ensure target sweetness is met within plus 0.1 bricks. After blending, the mixture is deaerated in a vacuum vessel. Liquid enters a chamber under reduced pressure, causing entrained oxygen and other gases to escape. The deaerated product is immediately cooled through a glycol-based plate chiller to a temperature just above 0 degrees Celsius, maximizing carbon dioxide solubility in the next step. The cold, deaerated blend is sent to the carbonation module. Here, liquid CO2 is introduced into the beverage via high-precision sparging rings located at the base of the carbonation tank. The tank operates under constant high pressure and uses recirculation pumps to keep the liquid moving over the gas interface, improving dissolution rates. Carbonation levels are controlled through feedback loops tied to gas volume analyzers that measure dissolved CO2 in real time. Once carbonated, the product is routed through pressurized transfer lines to filling buffer tanks. These tanks maintain positive pressure to prevent gas loss and are fitted with level sensors and pressure regulators. Container preparation runs in parallel. Empty aluminum cans or PET bottles are delivered via automated depalletizers that use vacuum pads or mechanical sweep arms to remove layers of containers and place them on conveyor systems. The containers pass through a cleaning unit where they are inverted and rinsed internally with filtered, ionized air or sterile water. Any residual moisture is blown off using high-velocity air knives. Clean containers proceed to the filling carousel. The filling system consists of a rotary filling machine with 60 to 120 heads, depending on capacity. Each container is raised into position against a filling valve. The system first applies counterpressure to match internal carbonation levels and prevent foaming. Filling valves open when pressure equalization is achieved. Product flows into the container through gravity or gentle pressurization. During fill, displaced gas vents through a return tube to maintain equilibrium. Fill volume is controlled by valve timing or volumetric flow measurement. Once filled, the valve closes and the container is lowered back to the conveyor. Capping occurs immediately after filling. For bottles, closures are delivered by an oriented cap feeder using centrifugal force. Caps are guided into a chute and pressed onto bottles by servo-controlled capping heads with adjustable torque settings. For cans, aluminum ends are fed into place from a lid magazine. A seamer head performs a double-fold operation, curling the lid's flange over the rim of the can and compressing the metal layers together to form an airtight seal. Sensors verify each seal, and containers with improper application are ejected from the line. Filled and sealed containers are conveyed through a vision inspection system equipped with high-speed cameras and LED backlighting. Algorithms analyze fill height, cap placement, and label orientation. Infrared sensors check for proper internal pressure via deformation profiles. Containers that do not meet specification are removed from the line using pneumatic pushers. Labeling systems vary by format. PET bottles pass through wraparound labelers that apply pressure-sensitive or roll-fed film labels. Servo motors control label placement, while rubber rollers press labels onto the surface. Cans use shrink sleeve applicators, where sleeves are dropped over the container body and pass through a heat tunnel. The tunnel uses either infrared or steam heat to contract the film evenly around the can. Label inspection units verify barcode readability, positioning, and design accuracy. The finished containers are then grouped into multi-packs. Bottles are sorted and arranged into clusters using pneumatic sweep arms and placed into molded plastic carriers or corrugated trays. Cans are conveyed into shrink wrapping units, where sets of 6, 12, or 24 are collated onto a moving belt. Polyethylene shrink film is dispensed over the groups and sealed at the edges. The packages move through a heated tunnel with recirculated hot air that shrinks the film tightly around the cans, securing them in a stable bundle. Multi-packs advance to the case packing area. Automatic case erectors unfold corrugated blanks into boxes and place them on a conveyor. Robotic gantries fitted with suction grippers pick up multiple multi-packs at once and lower them into open cases. Depending on format, cases may be closed using tape applicators or hot melt glue systems. Completed cases are scanned for contents, weight, and closure integrity using inline check weighers and vision systems. Palletizing begins with pallet dispensing. Wooden or plastic pallets are fed from a vertical stack onto a chain conveyor. Robotic palletizers, equipped with multi-axis arms, arrange cases on the pallet in interlocking patterns to maximize stability. Slip sheets may be inserted between layers using vacuum pick-and-place units. Once stacking is complete, the pallet moves into an automatic stretch wrapper. Here, the pallet is spun on a turntable while a film carriage applies tensioned polyethylene film around the load. The film is heat-sealed at the end of the cycle, and the wrapped pallet is discharged to a staging conveyor. Industrial ice cream production begins with the preparation of the liquid mix base. Raw ingredients used in the base include milk or milk solids, cream or anhydrous milk fat, sweeteners such as sucrose or glucose syrup, stabilizers, emulsifiers, and optional flavoring agents. Bulk liquid dairy components are stored in temperature-controlled stainless steel tanks connected to automated dosing lines. Milk fat content is measured using inline infrared sensors to meet formulation targets, typically between 8 and 12% depending on the product specification. Sweeteners such as granulated sugar or glucose syrup are stored in dry bins or heated tanks. Sugar is conveyed using auger screw feeders into blending tanks, while glucose syrup is pumped through jacketed pipelines at a regulated temperature between 45 and 60 degrees Celsius to maintain viscosity. Stabilizers and emulsifiers such as guar gum, mono and diglycerides, or carrageenan are added in precise quantities, using dry ingredient feeders with load cell controlled hoppers. All components are blended in high capacity, jacketed stainless steel mix tanks equipped with high shear agitation. Mixing durations and shear rates are pre-programmed and adjusted based on batch size and viscosity targets. The mixture is heated uniformly to 70-85 degrees Celsius using indirect steam in the jacket to fully dissolve solids and activate emulsification agents. This thermal processing step homogenizes the mixture and ensures complete dispersion of the fat phase. The hot mix is then passed through a homogenizer at pressures ranging from 1500 to 2500 psi. This high-pressure two-stage process reduces the size of fat globules, creating a stable emulsion and improving mouthfeel and overrun stability. Homogenization is measured and recorded by inline pressure transducers and flow meters. Once homogenized, the mix is immediately cooled to below 5 degrees Celsius using plate heat exchangers. The cooled mix is transferred to aging tanks and held between 2 and 5 degrees Celsius for a period of 4 to 24 hours, depending on product type. During aging, the fat crystallizes and proteins hydrate, which enhances body, texture, and whipping properties. Aging tanks are equipped with low-speed agitators to maintain uniformity without incorporating air. After aging, the mix is pumped into continuous freezers. These machines are equipped with scraper blades and barrel chillers. The mix enters at 2 to 5 degrees Celsius and is rapidly frozen as it moves through. The freezing cylinder cooled to approximately 20 to 25 degrees Celsius using ammonia or freon-based refrigeration systems. The freezing barrel incorporates air into the mix during agitation. The amount of air added is called overrun, typically maintained between 60 and 100% by volume using controlled air injection valves synchronized with pump speed. The partially frozen ice cream exiting the continuous freezer has a temperature of 5 to 7 degrees Celsius and a semi-solid texture. From this point, the product flow diverges based on packaging format. For bulk containers, the ice cream is extruded directly into tubs or pails using piston or rotary fillers. For single-serve novelties or molded formats, the product enters downstream portioning or molding stations. In extrusion-based forming systems, the semi-solid ice cream is extruded through stainless steel nozzles onto a moving stainless steel belt cooled to 40 degrees using cryogenic cooling elements. The belt carries the formed shapes under a quick freeze chamber where additional cold air is blown to firm up the shape. Inline sensors monitor form consistency and weight. Shapes are cut by ultrasonic or wire blades synchronized with belt movement. In molded systems, the ice cream is deposited into polycarbonate molds that travel on a carousel immersed in a brine solution held at 25 to 30 degrees. Product solidifies inside the mold within 8 to 12 minutes, depending on volume. Once hardened, sticks are inserted mechanically into the semi-solid mass using servo-driven arms. Demolding is achieved by briefly dipping molds into warm water baths and using pneumatic pistons to eject the bars. Fillings, inclusions, and variegates are added at multiple points. For layered products, rotary depositors add jams, caramel, or chocolate syrup between ice cream layers. Inclusion feeders dose chocolate chips, cookie pieces, or nut fragments into the flowing stream before extrusion using volumetric or gravimetric feeders. Variegates are added, using swirl nozzles or rotating spouts that inject sauces in spiral patterns into tubs. Enrobing stations apply chocolate coatings to frozen bars using curtain coaters or immersion tanks. Bars are transported on wire belts and pass through a curtain of liquid chocolate held at 30 to 35 degrees Celsius. Excess coating is blown off using air knives. Coated bars pass through a set zone where the chocolate is tempered and solidified using directed cold air streams. Toppings such as nut granules or cookie crumbs are applied to the wet coating via vibratory sprinklers before hardening. Once the shape is stabilized and the product fully frozen, packaging begins. Products are loaded into flow wrapping machines or form-fill seal machines. Printed film is drawn from reels, formed around the product, and sealed using heated jaws and pressure. Modified atmosphere flushing may be applied to reduce oxygen exposure. Each package is marked with batch codes and expiry dates via inkjet or laser printers. Packaged products proceed to check weighers and metal detectors for final inspection. Weighing systems use dynamic load cells to ensure each item is within +1% of target weight. Metal detectors with triple coil arrays scan for ferrous, non-ferrous, and stainless steel contamination. Rejected products are removed automatically from the line and logged in the manufacturing execution system. After inspection, individual packages are sorted into multi-packs or cartons using robotic collators and carton erectors. Units are loaded into retail-ready boxes, sealed with glue or tape and labeled with barcode identifiers. Cartons are stacked by robotic palletizers into programmed patterns based on load configuration and distribution route. Stretch wrapping machines secure pallets with film before warehouse transfer. In frozen storage, pallets are maintained at 25 degrees RC or colder. Pallet locations are mapped using barcode scanners integrated into warehouse management software. Products remain in frozen inventory for no more than the shelf life period assigned to each SKU. Rotation is enforced using first expiry, first out logic based on lot and production timestamp. The entire process is supported by centralized SCADA systems that monitor temperature, viscosity, pressure, weight, flow rate, air injection volume, and cooling intensity at every stage. Each unit of ice cream is fully traceable to its ingredient lots and production conditions through digitized batch records stored in the ERP system. The production of frozen yogurt in a factory begins with the preparation of the liquid mix base, which consists of dairy solids, sweeteners, live yogurt cultures, stabilizers, emulsifiers, and water. Each component is handled in isolated supply systems to ensure batch-to-batch consistency before integration. The mix formulation is calculated to achieve a target fat content of 2 to 4%, milk solids non-fat of 8 to 12%, and a final total solids content between 30 and 38%, depending on the product type. Bulk dairy ingredients, such as skimmed milk, whole milk, and cream, are stored in stainless steel, temperature-controlled silos or tanks held between 1 and 4 Arlingsi. These tanks are fitted with slow-speed agitators to prevent fat separation and sedimentation. From the tanks, ingredients are drawn through dedicated pipelines with volumetric flow meters that measure and regulate dosing rates with tolerances within plus 0.2%. Sweeteners such as sucrose, glucose syrup, fructose, or high fructose corn syrup are stored in either crystalline form or heated tanks depending on their physical state. Crystalline sugars are conveyed to mixing tanks via screw feeders or pneumatic conveyors, while liquid syrups are pumped through heated, jacketed pipes to maintain constant viscosity. The addition rates of each sweetener are determined by pre-programmed recipes in the batching software and are adjusted in real time based on inline refractometers measuring total soluble solids. Stabilizers and emulsifiers such as guar gum, carrageenan, mono and diglycerides, or cellulose derivatives are pre-blended into dry mixes and introduced using vacuum powder hoppers into blending tanks containing preheated water at 60-70 degrees Celsius. This temperature is critical for full hydration and dissolution. Agitation is applied using high-shear impeller mixers, ensuring uniform dispersion and hydration within 15 to 20 minutes. Viscosity is monitored continuously via inline rotational viscometers, and any deviation triggers automatic adjustment to the water feed rate or agitation speed. Once all ingredients are combined, the resulting mix is pasteurized using a continuous high-temperature, short-time HTST pasteurizer. The pasteurization process typically operates at 85 Celsius for 30 seconds to ensure microbial reduction without altering flavor or functional properties. The system includes balance tanks, timing pumps, regeneration sections, holding tubes, and cooling exchangers. Temperature probes and flow controllers verify that critical control parameters are met for every liter of mix. Any batch failing to meet time temperature integration is automatically diverted to a reject tank. Following pasteurization, the mix is homogenized in a two-stage homogenizer at pressures between 1500 and 2500 psi. The first stage breaks down fat globules to sub-micron sizes, promoting a stable emulsion, while the second stage disperses protein aggregates evenly throughout the mix. Homogenization ensures a smooth mouthfeel, prevents cream separation, and enhances the stability of the yogurt base during frozen storage. The homogenized mix is rapidly cooled to 4 degrees using a plate heat exchanger and transferred into agitated aging tanks. These stainless steel tanks have capacities ranging from 2,000 to 20,000 liters and are equipped with low-speed paddles to maintain uniform suspension without introducing air. The mix is aged for 4 to 24 hours depending on the formulation. During this aging period, fat crystallization and protein hydration take place, improving the whipping properties and final texture of the frozen yogurt. After aging, the next stage is inoculation with live yogurt cultures, a pre-prepared, freeze-dried culture blend containing specific strains of Lactobacillus, Bulgaricus, and Streptococcus thermophilus is rehydrated and activated in a sterile environment, then introduced into the aged mix in precise ratios. The inoculated mix is transferred to fermentation tanks equipped with temperature control systems. The mixture is held at 40, 43 degrees CS for 4 to 6 hours, during which lactic acid is produced, reducing pH from above 6.5 to around 4.5. The acidification process causes protein coagulation, giving the base its distinctive yogurt flavor and slightly thickened texture. Once fermentation reaches the target pH, it is immediately halted by cooling the mix to below 8 degrees Celsius. This temperature shock preserves the live cultures and stabilizes the flavor. From here, the yogurt base may be held in intermediate storage for up to 24 hours before being processed further. If flavorings or colorants are required, they are added post-fermentation to preserve the viability of the live cultures. These additives are introduced through inline dosing pumps, controlled by magnetic flow meters for precise delivery. The chilled fermented yogurt mix is transferred to the continuous freezing units. These industrial freezers use scraped surface barrel designs, where the yogurt base is frozen while being continuously agitated by rotating blades. The barrel wall is chilled to between 20 and 30 degrees using ammonia or freon-based refrigeration systems. The rotating blades prevent ice crystal growth by constantly scraping the frozen layer from the barrel wall and remixing it into the semi-frozen matrix. During freezing, air is incorporated into the mix to achieve a desired overrun of 30% to 60% by volume, much lower than regular ice. Cream to maintain the dense, creamy consistency associated with frozen yogurt. The air injection rate is precisely controlled using mass flow controllers and synchronized with product flow rate. The resulting product exits the freezer at a temperature of 5 to 7 degrees and has a soft serve consistency. If inclusions such as fruit pieces, chocolate chips, or granola clusters are required, they are introduced at this stage using rotary feeders or auger-based inclusion systems. These systems are calibrated to dispense particulate matter based on mass or volume per unit of frozen yogurt. Inclusions are mixed gently into the flow using low shear blending heads to avoid damaging texture or shape. Forming and portioning depend on the packaging format. For cups and tubs, rotary or piston fillers dispense the frozen yogurt into containers on an indexed conveyor line. Fill levels are verified using laser height sensors or load cells beneath the filling stations. The containers are then lidded using pick-and-place robots, followed by heat sealing or snap lid application depending on the package design. For stick products or novelty bars, the yogurt is extruded into polycarbonate molds mounted on a carousel or linear track. The molds pass through a 30 degrees C brine bath or air blast freezer for rapid hardening. Once the product reaches a core temperature of 18 degrees, sticks are inserted using servo-controlled plungers. The molded products are then released from the molds using brief exposure to warm water spray or ultrasonic demolding mechanisms. Products requiring enrobing are transferred to chocolate coating stations. Bars move on a mesh belt through a curtain of tempered chocolate or compound coating held at 32 to 34 degrees Celsius. Excess coating is removed using air knives, and toppings such as crushed nuts or cookie bits are sprinkled over the wet coating before it hardens in a subsequent cooling tunnel maintained at 15 degrees Celsius. Every unit, whether in cup, tub, or stick format, is passed through flow wrappers or form-fill seal machines. Packaging film is drawn over a forming collar, heat sealed along longitudinal and transverse axes, and printed with lot numbers and expiration dates using thermal inkjet systems. Products are checked on inline check weighers for mass accuracy, then metal detected using balanced coil systems capable of detecting contaminants down to 1.0 mmHg ferrous equivalents. Packaged frozen yogurt units are grouped into multi-packs or retail cartons using robotic pick-and-place systems. Cartons are sealed with hot melt glue and printed with barcodes and logistics identifiers. Palletizing robots stack cartons in programmed configurations. Each pallet is wrapped using rotary stretch wrapping machines and moved into blast freezers or deep storage warehouses. Frozen storage areas maintain air temperatures between 25 and 30 degrees Celsius, with controlled airflow to preserve texture and prevent ice recrystallization. Each pallet is tagged with barcodes that link to a warehouse management system, allowing full traceability of production date, ingredient lots, shift information, and packaging batch. The factory production of sorbet begins with the precise formulation of a base mix that typically consists of filtered water, fruit puree or juice concentrates, a combination of sugars, stabilizers, and acidulants. These ingredients are sourced in bulk and stored in isolated silos, refrigerated tanks, or powder silos based on their form and storage requirements. Before batching begins, each raw material is passed through automated intake stations where flow rate, weight, or volume is measured using mass flow meters or load cells to ensure formulation precision to the second decimal. The main batch tank is a large stainless steel jacketed vessel fitted with dual mode agitation, one high shear impeller and one slow speed anchor scraper to manage the simultaneous dispersion of powders and gentle circulation of the mix. The process begins by pumping deionized water into the tank. This water is processed through reverse osmosis filters to reduce mineral content and stabilize the flavor profile. Temperature of incoming water is held at 60 to 70 degrees Celsius to accelerate sugar dissolution and aid in the hydration of stabilizers later in the cycle. Fruit inputs, often high viscosity purees or concentrates, are pumped from cold storage tanks maintained at 4 gangs. These tanks are fitted with bottom-mounted paddle stirrers to prevent sedimentation of pulp or particulate matter. The fruit component is introduced via jacketed stainless lines with rotary lobe pumps that preserve particulate integrity and ensure steady laminar flow. Inline flow meters measure delivery in real time, adjusting valves based on programmable batch set points. Sweeteners are introduced in multiple phases depending on their type. Crystalline sugars, such as sucrose or dextrose, are stored in bulk bag unloaders and conveyed to the tank using vacuum-driven feeders or screw. Augers, passing through sieve screens to remove agglomerates. Liquid sweeteners, like glucose syrup or high fructose corn syrup, are pumped from preheated tanks through jacketed lines at temperatures between 40 and 60 degrees Celsius to reduce viscosity. All sugar additions are monitored using an inline refractometer, which continuously reads the brix level and automatically adjusts feed rates to ensure consistency in total soluble solids. Stabilizers and emulsifiers, including locust bean gum, guar gum, or pectin blends, are pre-dispersed into a slurry using a high shear induction system connected to a secondary mixing tank. The system uses a venturi-driven powder funnel that draws dry powders into a vortex of hot water, while shear blades break down clumps. The hydrated stabilizer solution is then metered into the primary batch tank over several minutes to allow for uniform dispersion. Viscosity is tracked by an inline rotational viscometer, while flow rate is synchronized with the agitator speed to prevent localized gelation. Acidulants are introduced once the temperature drops below 60 degrees Celsius to preserve their functional integrity. Citric acid and malic acid are most commonly used, added via microdosing pumps based on real-time pH feedback from inline probes. The typical pH target range for sorbet mix is between 3.4 and 4.2, depending on fruit type and desired tartness. Some blends may also include buffering salts or fruit-derived aromatic extracts, introduced in sub-gram quantities with gear-driven precision pumps. Once the mix is fully blended, the entire volume is passed through a plate or tubular heat exchanger for pasteurization. The product is heated to between 82 and 90 degrees Celsius for a holding period of 20 to 30 seconds using a hot water loop on the heating side of the exchanger. Flow rates are calibrated to ensure that each liter achieves the required thermal profile. Temperature probes at the inlet, outlet, and holding tube ensure compliance with the time temperature curve. Any deviation from set points automatically diverts the mix to a rework tank using pneumatically controlled valves. Following pasteurization, the mix is rapidly cooled to 4 degrees Celsius using chilled glycol in the final section of the exchanger. It is then pumped to aging tanks, insulated, vertical stainless steel silos with gentle agitators. The mix is held for 4 to 24 hours, depending on stabilizer type, allowing the hydration of hydrocolloids and maturation of flavor. During aging, key metrics including Brix, viscosity, pH, and color are measured at regular intervals using inline and lab-based sampling. After aging, the mix is transferred to continuous freezers for dynamic freezing. These are horizontal barrel-type scraped surface heat exchangers with internal rotors spinning at high speed. The internal barrel is cooled by ammonia or freon-based refrigerant, keeping the wall temperature at 25 degrees Celsius to 30 degrees Celsius. The mix is pumped into the barrel at 4 degrees Celsius and partially frozen in under 30 seconds. Rotor blades scrape frozen mix from the walls, maintaining even temperature distribution and preventing ice crystal buildup. At this stage, air is injected into the freezing chamber to achieve controlled overrun. For sorbet, overrun levels are typically between 10 and 30%, maintained using mass flow controlled air injection, synchronized with product throughput. Air pressure, temperature, and flow rate are logged continuously. The exit temperature of the product from the freezer is typically 5 degrees Celsius to 7 degrees Celsius, with a soft serve consistency suitable for depositing. At the point of extrusion, some product formats receive inclusions or variegates. For inclusion, dry or semi-moist elements like fruit pieces, citrus peel, or coconut shreds are fed through a belt-based dosing unit with weigh cell feedback. The feeder aligns with the product stream and deposits inclusions just before it enters the filler. Variegates, such as raspberry swirls or mango sauce, are injected via multi-nozzle swirl heads using positive displacement pumps, synchronized with container indexing to create layered or spiral visual effects. The filling system uses rotary or linear piston fillers with programmable dose volumes. Fill heads descend into the container, release the product in a bottom-up motion to prevent air entrapment, and retract at the end of the fill cycle. Laser height sensors verify the final fill level to ensure consistency. For products with decorative topping, a secondary depositor adds surface sources, fragments, or textured swirls before lidding. Filled containers are sealed with pre-cut lids or heat-sealed films. Lidding stations use servo-driven arms and apply uniform pressure to ensure adherence. Date coding and batch marking are applied using thermal inkjet or CO2 laser systems immediately after sealing. Each pack is passed through a metal detector, which uses multi-frequency coils to detect foreign metallic objects within the sealed product. Immediately post-packaging, the product enters the hardening tunnel. This is a spiral or straight belt blast freezer, where ambient air temperature is held at 35 to 45 degrees Celsius. Air is circulated at high speed to ensure fast freezing rates. Dwell time inside the tunnel ranges from 30 to 90 minutes, and the goal is to reduce the core temperature of each unit to below just 18 degrees Celsius. Faster hardening reduces ice crystal size and improves long-term texture stability. Core temperatures are verified by infrared sensors or penetrating thermocouples on randomly sampled units. Hardened products are conveyed to automated carton packers. A vision system identifies each container's orientation and positioning. Robotic arms equipped with suction grippers or mechanical clamps group units into clusters and load them into pre-erected cartons. Cartons are sealed using hot melt adhesive or tape, then labeled using a print and apply labeling system. The label includes SKU identifiers, lot number, date, and logistics barcodes. Cartons are then routed to the palletizer. Layers of cartons are stacked according to a programmed pattern to optimize pallet stability and maximize transport efficiency. Stretch wrapping machines encase each pallet in multi-layered film with preset tension profiles to secure the load during transport. Pallets are labeled with SSCC codes and sent to deep freeze storage, where ambient temperature is maintained between 25 and 30 degrees C. Storage location is recorded in a warehouse management system using RFID or barcode scanning. Each batch of sorbet is traceable through electronic production records, linking ingredient lots, formulation parameters, processing times, and packaging data. Digital records include metrics for pasteurization, Brix values, overrun, pH, freezing rate, fill weight, inclusion density, and packaging inspection results. Production lines are modular and allow for multiple flavor variants and packaging formats. Line changeovers are performed by CIP, clean-in-place cycles, product purges, and recipe uploads via the SCADA interface. Automated valves and sensor diagnostics reduce downtime between batches. Lines may produce up to 8,000 litres of finished sorbet per hour, depending on viscosity, inclusion complexity, and packaging speed.